Hello there, and welcome to Physics with William, where curiosity settles into a comfortable chair and science takes the long, quiet road through the universe. Tonight, we're going to spend some time with one of the most famous particles in modern physics, a particle that made headlines around the world, caused physicists to cheer in control rooms, and somehow managed to sound both extremely important and slightly suspicious, the Higgs boson. You may have heard it called the God particle, though many physicists would probably make a face at that name while quietly moving their tea to a safer distance. It is dramatic, certainly. It is catchy, undeniably. But it also gives the wrong impression, as if the Higgs boson is a tiny divine bead hiding somewhere inside matter, handing out mass like a very serious cosmic librarian. The real story is stranger, subtler, and in many ways much more interesting. So tonight we're asking a gentle but surprisingly deep question. What is the Higgs boson really made of? Not in the way we might ask what a chair is made of, or what a biscuit is made of, though I will admit a biscuit is usually the more emotionally urgent question. We're asking what it means for a particle to exist at all. We're asking whether the Higgs boson is a little object, a tiny ball, a speck of stuff, or whether it is something else entirely. Because in the world of modern physics, particles are not quite the solid little grains we imagine. They are not miniature marbles rolling through empty space. They're excitations, disturbances, little packets of activity in deeper invisible things called fields. And the Higgs boson is one such disturbance in one of the most important fields we know, the Higgs field. But there is no need to rush there just yet. The universe has waited 13.8 billion years for us to ask these questions, so it can probably give us a few minutes to get comfortable. Wherever you are listening from, perhaps in a quiet room, perhaps with the lights low, perhaps while the rest of the world is busy doing whatever the rest of the world does when we are trying to relax, I wonder what kind of matter is around you right now. Maybe a blanket, a pillow, a cup of tea, a phone resting on the table, the floor beneath you, the air moving softly in and out of your lungs. All of it has mass. All of it resists being pushed around. All of it belongs to a universe where things have weight, shape, structure, and presence. And hidden behind that ordinary fact is one of the great discoveries of 20th and 21st century physics. Where in the world are you listening from tonight? And what is the nearest object to you that suddenly feels a little more mysterious now that you know its mass is not quite as simple as it seems? It is a pleasant thought, in a way, that every room is full of physics. You do not need a particle accelerator in your bedroom to be surrounded by deep questions. Though if you do have one, please make sure it is switched off before sleep, and perhaps check the warranty. The fabric of reality is already here, quietly doing its work in the background. The atoms in your body, the electrons in the walls, the particles in the dust floating through a beam of light, all of them are taking part in a hidden arrangement that gives the world its familiar firmness. If you find this kind of quiet wandering through physics soothing, or if it gives your thoughts somewhere calm to rest at the end of the day, I would be very grateful if you gave the video a like and subscribed. It helps this little corner of gentle science find others who might also enjoy drifting through the universe without being shouted at by it. And if the Higgs boson ends up keeping you awake with curiosity, I do apologise. We will try to keep it soft, steady, and friendly, even when the science becomes wonderfully strange. To begin, it helps to notice how natural it is to imagine matter as being made of smaller and smaller bits. A wooden table is made of wood. Wood is made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms are made of electrons and a nucleus. The nucleus is made of protons and neutrons. Protons and neutrons are made of quarks. This is the kind of story many of us learn at school, a story of taking things apart like a set of nesting boxes. Open one box and there is a smaller box inside. Open that one and there is another. Keep going, and perhaps eventually you reach the final little pieces of everything. It is a tidy picture, and the human mind does enjoy a tidy picture. The universe, unfortunately, has never been under any obligation to be tidy. The Higgs boson does not fit neatly into that everyday picture. It is not, as far as we know, made of smaller ordinary pieces in the same way a proton is made of quarks. It is not a tiny bag containing even tinier ingredients. It is considered an elementary particle, which means that in our best current understanding, it has no known internal structure. That statement sounds simple, but it carries a lot of weight. When physicists say elementary, they do not mean that they have looked inside and found a little label saying empty. They mean that every experiment so far treats it as if it has no smaller parts. It behaves like a fundamental excitation of a field, not like a composite object built from hidden components. If that feels a little slippery, that is not your fault. It is slippery. Particle physics is full of ideas that look simple from a distance, then become quite misty when you step closer. A familiar object has a surface, a size, and a location you can point to. A tennis ball is here and not there. A crumb on a plate is small, but still very much a thing. You can imagine splitting it, at least until it becomes too tiny to manage, and everyone involved begins to regret the experiment. Particles in quantum physics are different. They do not behave like little solid beads with neat edges. An electron, for example, is not a miniature planet orbiting an atomic nucleus like a moon. It is described by quantum fields and probabilities. It has properties such as mass and electric charge, but it does not have a little painted surface. It is less like a speck of dust and more like a precise event that nature allows to happen. The Higgs boson belongs to this same family of strange quantum things, but with a special role. It is linked to the Higgs field, a field that fills all of space. That phrase can sound almost too casual, as if we have just said there is wallpaper everywhere in the universe, but a field in physics is not wallpaper. It is something that has a value at every point in space. The electromagnetic field is one example. It is responsible for light, radio waves, magnets, electricity, and many of the little shocks that make you distrust door handles in winter. The electron field is another. Every electron is an excitation of that field. In this view, the universe is not made mainly of tiny things sitting inside emptiness. It is made of fields, and what we call particles are ripples or vibrations in those fields. This is where the Higgs boson begins to make more sense, though perhaps only after making everything else feel less solid for a moment. If the Higgs field is like an invisible presence spread through space, then the Higgs boson is a ripple in that field. Not a ripple like water exactly, because water is made of molecules and the Higgs field is not water. Still, as a gentle image, it helps. Imagine a calm surface that can be disturbed. If something puts energy into it in just the right way, a wave appears. The wave is not separate from the surface, it is the surface moving. The Higgs boson is not a little object floating inside the Higgs field, it is the Higgs field excited in a particular quantum way. This is why asking what the Higgs boson is made of can be tricky. In ordinary language, made of means ingredients. A cake is made of flour, eggs, sugar, and whatever else one adds while pretending not to eat the mixture from the spoon. A mountain is made of rock. A cloud is made of tiny droplets or ice crystals. But an elementary particle is not necessarily made of ingredients. It is made, if we can use that word carefully, of field activity. It is a quantized excitation. That means nature allows the field to carry energy in discrete packets, and one packet of Higgs field excitation is what we call a Higgs boson. No flour, no eggs, no hidden clockwork, and almost certainly no tiny instruction manual folded inside. The discovery of the Higgs boson in 2012 was not a case of scientists seeing it directly through a microscope. There is no photograph of a Higgs boson sitting politely for the camera. The Higgs boson is far too unstable for that. It appears for an incredibly brief moment in high-energy particle collisions and then decays into other particles. Physicists at the Large Hadron Collider did not catch it like a butterfly in a net. They created conditions where Higgs bosons could be produced, then studied the patterns left behind after they vanished. It was a little like hearing a single quiet note in a storm by studying how the windows trembled afterward. Not easy, not quick, and not the kind of thing one should attempt before breakfast without proper funding. The fact that the Higgs boson decays so quickly also adds to its mysterious reputation. We are used to objects that stay put. A stone remains a stone unless something happens to it. A chair may creak, but it usually does not vanish into a spray of other furniture. The Higgs boson, by contrast, exists briefly and transforms. It is heavy by particle standards, unstable, and difficult to produce. It is not part of ordinary matter in the way electrons and quarks are. The atoms in your body do not contain Higgs boson sitting inside them like raisins in a pudding. That is an important point. The Higgs field is everywhere, and many elementary particles interact with it. But the Higgs boson itself is not a permanent ingredient inside everyday matter. It is more like a detectable ripple that proves the field is real. This distinction matters because it helps clear up a common misunderstanding. People sometimes hear that the Higgs boson gives particles mass and imagine tiny Higgs bosons sticking to everything, weighing them down like dust on a shelf. That is not quite right. The Higgs boson is evidence of the Higgs field. It is the field, not a cloud of Higgs bosons, that is involved in giving certain elementary particles their mass. The field is present even when no Higgs bosons are flying around. In fact, that is part of what makes it so unusual. Most fields are calm at their lowest energy state. The Higgs field, however, has a non-zero value even in empty space. Empty space, in this sense, is not simply nothing. It has structure, it has properties, it has a kind of quiet background condition that particles move through. That idea changes how we think about emptiness. We tend to imagine empty space as blank, as nothing at all. Remove the planets, remove the stars, remove the gas and dust, and surely what remains is a perfect void. But modern physics tells us that the vacuum is not a dull absence. It is more like the lowest possible state of many fields. It may look empty because there are no particles present, but the fields are still there. The Higgs field is still there. The rules of reality are still quietly in place. Space is not a stage made of nothing. It is more like a deeply active system that only appears still because we are not looking at it in the right way. And this is where the question becomes even more interesting. If the Higgs boson is an excitation of the Higgs field, and if the Higgs field fills space, then what is the field made of? At this point, physics becomes cautious. In the standard model, the Higgs field is fundamental. That means it is not described as being made of smaller things. It is one of the basic ingredients of the theory. The Higgs boson, as its ripple, is also treated as fundamental. But science is not a finished book placed neatly on a shelf. It is a working notebook, full of crossed out lines, careful measurements, and the occasional coffee stain. There are ideas beyond the standard model suggesting that the Higgs might not be truly elementary after all. Perhaps it is composite. Perhaps it is connected to deeper fields. Perhaps it is a doorway into a richer structure that we have not yet uncovered. But so far, experiments have found no clear evidence that the Higgs boson is made of smaller parts. That is a wonderful kind of answer, because it is both firm and unfinished. As far as we know, the Higgs boson is not made of anything smaller. It is a fundamental ripple in the Higgs field. But as far as we wonder, it might still be part of a deeper story. Physics often lives in that space between what we know and what we suspect. The Higgs boson is not just a particle we found. It is a question we are still learning how to ask properly. To understand why it matters so much, we need to move slowly into the older problem that made the Higgs field necessary in the first place. Why do particles have mass at all? That may sound obvious at first. Things have mass because they are made of stuff. A bowling ball is heavier than a feather because it contains more matter packed into it. A suitcase becomes heavier when you put more clothes in it, especially if you're the sort of traveller who packs as though moving permanently to a mountain hut. But at the level of elementary particles, mass is not so obvious. Some particles have mass, some do not. The photon, the particle of light, has no mass. The electron has a small mass. The top quark has a very large mass compared with other elementary particles. Why should that be? What decides the difference? Before the Higgs mechanism was developed, this was a serious puzzle. The laws describing particle interactions had a beautiful symmetry, but simply adding mass to certain particles would break the mathematical structure that made the theory work. Physicists needed a way for particles to behave as if they had mass, without ruining the deep consistency of the theory. The Higgs field provided that way. Particles that interact strongly with the Higgs field acquire more mass. Particles that interact weakly acquire less. Particles that do not interact with it in that way, such as photons, remain massless. This is a simplified version, but it gives the right flavour. Mass is not merely a lump of substance. For elementary particles, mass can arise from interaction with a field that exists everywhere. That is a strange idea, but it is not completely beyond everyday comparison. Imagine moving through different environments. Walking through air is easy. Walking through water is harder. Walking through thick mud is harder still and far less dignified. The resistance you feel depends on how you interact with the medium around you. Now, this is only an analogy, and like all analogies in physics, it should not be asked to carry heavy furniture upstairs. The Higgs field is not mud, and particles are not little people wading through it. But the image can help us feel the basic point. The properties of a particle are not only about the particle by itself, they are also about its relationship with the fields around it. The Higgs boson, then, is not the thing that gives your chair its mass in a simple, direct way. Most of the mass of ordinary matter actually comes from the energy binding quarks together inside protons and neutrons through the strong nuclear force. The Higgs field gives mass to elementary particles such as quarks and electrons, but the mass of everyday objects is mostly a richer story involving energy inside atomic nuclei. This is one of those details that makes the common headline a little too neat. The Higgs is crucial, yes. Without it, the universe would be profoundly different. But it is not the only source of mass in the world around us. Reality rarely lets one idea take all the credit. Still, without the Higgs field, the universe as we know it would not hold together in the same way. Electrons would not have their familiar mass. Quarks would not have theirs. Atoms would not behave as they do. Chemistry would be unrecognizable. Stars, planets, oceans, cells, and sleepy listeners enjoying physics at night would not exist in the same form. The Higgs field is not a decorative extra. It is woven into the basic architecture of the world. The Higgs boson is important because it is the visible clue, the measurable ripple, the footprint that told us the field was really there. So when we ask what the Higgs boson is really made of, we are beginning with a question that sounds simple and ends up leading us into the deepest language of modern physics. It asks us to trade the idea of solid little building blocks for a universe of fields. It asks us to rethink emptiness. It asks us to accept that a particle can be less like a tiny object and more like a brief, precise disturbance in something spread everywhere. And it asks us to be comfortable, at least for a while, with an answer that says, as far as we can tell, it is not made of smaller stuff at all. That can feel unsatisfying at first. We like ingredients. We like recipes. We like being able to say this is made of that. But nature does not always answer in the grammar we prefer. Sometimes when we ask what something is made of, nature replies by showing us a field. Sometimes it tells us that the thing we thought was an object is really an event. Sometimes the smallest pieces are not pieces. They are patterns of activity, stable enough to be named, measured, and placed into our theories, but not solid in the ordinary sense. And that is where our path really begins. Not with the Higgs boson alone, but with the strange emptiness around it. Because before we can understand what kind of thing the Higgs boson is, we need to understand the stage on which it appears, a stage that is not empty, not passive, and not quite like anything our everyday senses were built to imagine. Empty space, as it turns out, is one of the busiest quiet places in the universe. It holds fields, possibilities, fluctuations, and the hidden conditions that allow particles to exist at all. So let us settle a little deeper and step gently toward that invisible background. where nothing is not really nothing, and where the story of the Higgs begins to take shape. Empty space sounds like it ought to be simple. It sounds like the easiest thing in the universe to understand. After all, if you take away the stars, the planets, the dust, the light, the air, the atoms, the stray crumbs from a late-night snack, what is left should be nothing. A blank, a pause, a cosmic room with all the furniture removed. And for a long time, that was more or less how people imagined it. Space was the empty container where things happened. Matter was the interesting part. Space was just the gap between objects, the silence between notes, the place where planets could move without bumping into celestial clutter. But modern physics has a habit of taking the simplest words and making them quietly mysterious. Empty is one of those words. Nothing is another. They sound so clean and final, as if we can simply point to a region of space and say, there is nothing there, and the universe will politely agree. It does not. The closer physicists have looked at empty space, the less empty it has become. Not because it is secretly full of dust or invisible mist or tiny mechanical parts, but because the very idea of emptiness changes when we stop thinking of the universe as a collection of objects and begin thinking of it as a collection of fields. This matters deeply for the Higgs boson, because the Higgs story is not really a story about a particle hiding inside matter. It is a story about what space itself is like, even before you put anything in it. The Higgs field is not stored inside atoms. It is not packed into protons like filling in a pastry. It is not sprinkled through the universe as a fine powder. It is part of what we mean by the physical vacuum, the lowest energy state of a field that is present everywhere. And that is where the strangeness begins. The Higgs boson appears only when that field is disturbed in a particular way, but the field itself is there all the time. It is there in the space between galaxies. It is there in the space inside atoms. It is there in the room around you now, quietly contributing to the basic properties of the particles that make up your hands, your blanket, your cup, and the device playing this voice. The first step is to let go of the idea that empty space is just an absence. In everyday life, empty means available. An empty glass can be filled with water, an empty chair can be sat on, an empty drawer can finally receive all the mysterious cables we keep, just in case they are important, though no one has seen the device they belong to since about 2 house moves ago. But in physics, empty space is not merely unused space, it is a physical state. It has measurable properties, it can expand, it can bend, it can carry waves, it can contain fields even when there are no particles present. It is not nothing in the philosophical sense. It is the vacuum, and the vacuum is a much more interesting creature. We can approach this gently by thinking about light. Imagine a radio wave travelling from a distant transmitter to your home. It crosses what may seem like empty air, or even empty space, but it is not carried by a material substance in the old-fashioned sense. There is no hidden jelly through which it wiggles. Instead, the wave is a changing electromagnetic field. That field exists throughout space, and when it is disturbed, the disturbance travels as light, radio waves, microwaves, X-rays, and all the other forms of electromagnetic radiation. A photon, in modern language, is a quantum excitation of the electromagnetic field. It is not a little pebble flying through a void in quite the ordinary way. It is a packet of field activity. Once that idea is allowed into the room, it quietly rearranges the furniture. If light is a ripple in a field, perhaps other particles are also ripples in fields. That is exactly the picture modern particle physics gives us. There is an electron field. There are quark fields. There are fields associated with the forces of nature, and there is the Higgs field. These fields are not made of ordinary matter. They are not substances in the old mechanical sense. They are more basic than that. They are the underlying things whose excitations show up to us as particles. In this view, the universe is less like a vast empty box filled with tiny beads, and more like an enormous layered invisible set of fields, each capable of trembling in its own precise way. Of course, saying that does not instantly make it easy to picture. Our brains evolved to deal with fruit, stones, weather, faces, paths, and the occasional suspicious rustling in the bushes. They did not evolve to picture quantum fields. If quantum fields feel difficult to imagine, that is perfectly normal. They are not part of ordinary sensory experience. You cannot reach out and touch the electron field as a separate thing. You cannot smell the Higgs field, which is probably for the best, because the universe already has enough things to worry about. But you can observe the consequences of these fields. You can measure electrons. You can detect photons. You can infer the presence of the Higgs field by producing and measuring Higgs bosons. Physics often works this way. We do not always see the underlying thing directly. We see what it makes possible. The old idea of a truly empty void became especially troubled with the arrival of quantum mechanics. Quantum theory tells us that fields cannot simply sit in perfect stillness in the way we might imagine. Even in their lowest energy state, they retain a kind of unavoidable activity. This is sometimes described as vacuum fluctuation, though that phrase can be misunderstood. It does not mean that little particles are constantly popping in and out of existence like nervous rabbits in a magician's hat, at least not in the simple cartoon version often repeated. It means that quantum fields have uncertainty built into them. Their lowest energy state is not a perfectly frozen state of nothingness. There is still structure. There are still measurable effects. One famous example is the attraction that can occur between two extremely close metal plates in a vacuum. The details are delicate, but the broad idea is that the quantum vacuum is not featureless. Its field modes are affected by boundaries, and that can produce a tiny but real force. This is one of those experimental hints that empty space is not merely emptiness. It has behavior. It can respond to conditions. It can push, pull, and influence the world in ways that are subtle but measurable. If that seems unfair to the word empty, perhaps it is. Physics has never been especially kind to ordinary words. Another example comes from the way particles behave in the vacuum around them. In quantum field theory, particles are never fully isolated from the fields with which they interact. An electron, for instance, is surrounded by effects from its interaction with the electromagnetic field and other quantum fields. Again, it is important not to picture this too literally as a tiny electron wearing a fluffy coat of miniature particles. The mathematics is much more precise and much less woolly. But the central point is that the vacuum influences measurable properties. What we call a particle is partly defined by how it exists within the network of fields around it. This is the world into which the Higgs field enters. Among all these fields, the Higgs field has a particularly unusual feature. Its lowest energy state is not one where its value is simply zero. Instead, even empty space has a non-zero Higgs field value. In plain words, the Higgs field is switched on everywhere, even in the vacuum. It is not switched on by stars or galaxies or atoms. It is just part of the state of the universe. This is very different from, say, the electromagnetic field around you, which can be stronger or weaker depending on charges, currents, magnets, and radiation. The Higgs field has a background presence that fills space uniformly, as far as our measurements can tell. This is the strange emptiness that matters for mass. Many elementary particles interact with that ever-present Higgs field. Through that interaction, they behave as if they have mass. Some interact more strongly and have larger masses. Some interact more weakly and have smaller masses. Photons do not acquire mass from the Higgs field in this way, which is why light can travel as it does. The details are subtle, but the main idea is gentle enough to hold. The vacuum is not an empty stage. It has a condition built into it, and that condition affects the properties of particles moving through it. Notice how different this is from the older picture of mass as simply the amount of stuff inside something. At everyday scales, that picture works well enough. A bag with more potatoes is heavier than a bag with fewer potatoes, unless someone has been unusually ambitious with the size of the potatoes. But for elementary particles, mass is not explained by smaller bits packed inside them. An electron is not heavy because it contains little grains. As far as we know, it has no internal ingredients. Its mass is tied to its relationship with the Higgs field. The particle is fundamental, but its mass arises through interaction. That is a different kind of explanation, one that shifts the focus from hidden material parts to the structure of the vacuum itself. This also helps us understand why the Higgs boson is not simply floating around inside everything. The field is everywhere, but the boson is an excitation of that field. A calm field can fill all of space without producing actual Higgs bosons in the ordinary sense. To create a Higgs boson, you must put enough energy into the Higgs field in a concentrated way. That is one reason the Large Hadron Collider was needed. It slams particles together at extraordinary energies, creating tiny, brief conditions where the Higgs field can be excited strongly enough for a Higgs boson to appear. Then the Higgs boson almost immediately decays, leaving behind other particles that detectors can measure. The boson is fleeting. The field is persistent. There is something almost humbling about that. The famous particle, the one that received applause, headlines, and more dramatic nicknames than it ever asked for, is a momentary ripple. The quieter field behind it is the deeper presence. In everyday thinking, we often give attention to visible events and overlook the background that makes them possible. We notice the wave, not the ocean. We notice the spark, not the air. We notice the music, not the silence that lets it be heard. Physics, in its careful way, often asks us to look at the background, and in this case, the background turns out to be one of the most important parts of reality. But we should be careful with the phrase fills space. The Higgs field is not like a liquid filling a bottle. If it were a liquid, we might ask what it is made of, where its molecules are, how thick it is, whether it splashes, and whether one should bring a towel. That picture breaks down quickly. A field is not a substance spread through space in the usual material sense. It is a physical entity whose value is defined at every point in space. That sounds abstract, but fields are not optional decorations in modern physics. They are the working foundation. We know fields are real, or at least as real as anything in physics can be said to be, because their effects are consistent, measurable, and predictive. Gravity offers another useful comparison, though it belongs to a different theoretical framework. In general relativity, gravity is not simply a force pulling objects across empty space. It is related to the curvature of space-time itself. A planet orbits not because an invisible rope tugs it in a simple Newtonian way, but because matter and energy shape the geometry around them. Here again, the background is not passive. Space and time are not merely a box and a clock. They have structure and behaviour. Put this together with quantum fields, and the old empty stage becomes very hard to defend. The universe is less like a theatre and more like a living rule book, with the rules themselves woven into every location. The vacuum can also change. That is a quietly astonishing fact. In some areas of physics, scientists study different possible vacuum states, meaning different ways fields might settle into their lowest energy arrangements. The vacuum we live in may be stable, or it may be only long-lived, depending on details that physicists continue to investigate. This is not something to lose sleep over. The universe has been doing reasonably well for billions of years, apart from a few local inconveniences like exploding stars and alarm clocks. But it does show that the vacuum is not simply nothing. It has a state, it has properties, it may even have history. The Higgs field is central to this because its value in the vacuum affects the masses of elementary particles and the structure of the forces. If the Higgs field had settled differently, the universe might have been profoundly unlike ours. Electrons might have had different masses. Quarks might have behaved differently. Atoms might not have formed in the same way, or at all. Chemistry could have failed to become chemistry. Stars might not have burned as they do. The quiet background value of one field helps decide whether the universe can build complex structures. That is a remarkable thing to say about what we might casually call empty space. This is where the Higgs boson becomes a messenger. It tells us about the shape of the Higgs field and the nature of its vacuum state. When physicists measure the Higgs boson's mass, how often it decays in different ways, and how it interacts with other particles. They're not simply cataloguing one more particle for a cosmic stamp collection. They're testing the structure of the Higgs field itself. They're asking whether it behaves exactly as the standard model predicts, or whether tiny deviations might point toward deeper physics. If the Higgs boson were found to have unexpected properties, it could suggest that the Higgs field is connected to new particles, new forces, or a more complicated layer beneath the theory we already know. So far, the Higgs boson looks very much like the standard model expected. That is both satisfying and slightly annoying, depending on how hungry one is for new physics. Physicists are pleased when a theory works, of course. A successful prediction is a beautiful thing. But they are also aware that the standard model is not the final story. It does not explain gravity at the quantum level. It does not explain dark matter. It does not fully explain why the universe contains more matter than antimatter. It leaves many questions open. The Higgs boson sits right in the middle of this tension. It completes one part of the standard model beautifully, yet it may also be the doorway to what lies beyond. One reason physicists care so much about whether the Higgs is elementary is that elementary scalar particles are unusual. Scalar here means that the Higgs field has a simple kind of value at each point, not a direction like some other fields. In the standard model, the Higgs boson is the only elementary particle of its kind. That makes it special, but also puzzling. Its mass is sensitive in theoretical calculations to effects from very high-energy physics. Many physicists have wondered why it has the mass it does rather than being driven to something much larger. This puzzle has inspired many ideas, including supersymmetry, composite Higgs models, and other proposals. We do not need to wander through all of those in detail just yet. For now, it is enough to know that the Higgs field is not merely another field on the list. It is a clue, and perhaps a challenge. The vacuum, then, is not a boring absence. It is the home of the fields. It is the setting of their lowest energy behaviour. It is where the Higgs field quietly takes on the value that helps make particles massive. It is where quantum uncertainty prevents perfect stillness. It is where the known universe gets many of its basic properties. Calling it empty is like calling a sleeping cat inactive. It may look still, but there is a great deal going on beneath the surface, and at any moment it may decide to become dramatically relevant. This also changes how we might imagine the space around us. The room you are in is not simply a container holding furniture and air. Even if all the air were removed, even if the room were cooled and shielded and made as empty as technology allowed, the quantum fields would remain. The Higgs field would remain. The electron field would remain. The electromagnetic field would remain. The possibility of particles would remain. Empty space is not the absence of reality. It is reality in one of its quietest forms, and perhaps that is the most useful way to think about it. The vacuum is quiet, not blank. It is quiet in the way a sleeping city is quiet, with structures, systems, and hidden activity still present. It is quiet in the way a piano is quiet before a note is played, not because music is impossible, but because the instrument is waiting. When enough energy is added in the right way, fields can produce particles. When a field is disturbed, a quantum can appear. When the Higgs field is struck hard enough in a particle collision, the Higgs boson can briefly rise from the vacuum like a tiny announcement that the field was there all along. That is why the question of what the Higgs boson is made of cannot be separated from the question of what empty space is made of, or more carefully, what physical structure remains when particles are removed. The Higgs boson is made of Higgs field excitation, and the Higgs field belongs to the vacuum itself. Not vacuum as nothing, but vacuum as the underlying state of fields. This is a very different answer from the one our everyday instincts expect. We ask for ingredients and receive a lesson about emptiness. We ask for the inside of a particle and are led into the nature of space. From here, the next step is to become more comfortable with fields themselves. Because if fields are the deeper language of modern physics, we need to understand what they are doing before particles ever appear. Before electrons are detected, before photons are emitted, Before a Higgs boson briefly flashes into existence and vanishes into other particles, there are fields. They are not objects in the familiar sense, and yet they are not imaginary. They are the quiet machinery of the world, spread through every region of space, capable of carrying energy, creating particles, and shaping the rules by which matter behaves. The Higgs field is one of them, but not the only one, and to understand why its ripple is so important, we need to spend a little longer with the idea that particles are not the beginning of the story. The fields are. Before we can really understand the Higgs boson, we need to step back from the particle itself and spend a little time with the deeper idea that made modern physics so different from the older picture many of us carry around in our heads. It is very natural to imagine the universe as a place filled with things. Stars, stones, atoms, electrons, photons, little bits here and there, moving through space like dust in a sunbeam. That picture is not useless. In everyday life it works very well. A mug is on the table, a book is on the shelf, a cat is on the keyboard, usually at the exact moment you need the keyboard most. We understand the world through objects because objects are what our senses are built to handle. But the world of fundamental physics does not begin with objects in quite that way. At the deepest level described by our best-tested theories, the basic ingredients are not tiny solid things sitting in empty space. They are fields. The particles we talk about are what fields look like when they are excited in particular ways. That may sound like physics quietly replacing one mystery with another, which, to be fair, it does sometimes do. But it is also one of the most powerful and successful ideas in all of science. It allows us to describe light, electricity, magnetism, matter, radiation, particle collisions, and the Higgs boson itself with remarkable precision. A field, in the simplest possible terms, is something that has a value everywhere in space. That value might be simple or complicated. It might point in a direction. It might change with time, it might carry energy, it might interact with other fields. But the important idea is that a field is not just a thing located in one place, it extends across space. If you have ever seen a weather map showing temperature over a country, you have already seen a simple kind of field. Every location has a temperature. Some places are warmer, some are colder, and the pattern changes throughout the day. The temperature is not an object you can pick up, yet it is physically meaningful. It tells you whether to wear a coat, open a window, or pretend that walking outside in the rain builds character. A magnetic field is another familiar example. You cannot see it directly, but you can see what it does. Place iron filings near a magnet, and they arrange themselves in curved patterns. The filings are not creating the field, they are revealing it. The field was already there, influencing the space around the magnet. A compass needle turns because it responds to the magnetic field around it. You do not need to imagine tiny invisible strings pulling the needle. The field is the thing that tells the needle which way to align. In this sense, a field is not a decorative idea added on top of reality. It is part of how reality behaves. The electromagnetic field is especially important because it helped physicists learn to take fields seriously. In the 19th century, scientists such as Michael Faraday and James Clerk Maxwell developed the idea that electric and magnetic effects were not separate curiosities, but parts of one unified field. Faraday imagined lines of force filling space. Maxwell turned that picture into a precise theory, showing that changing electric and magnetic fields could travel as waves. Those waves turned out to be light. That was a tremendous shift. Light was not simply a stream of little particles in the old sense, nor a vibration in some ordinary material medium. It was a self-sustaining wave in the electromagnetic field. This changed the role of empty space. Space was no longer just a blank gap across which forces somehow reached. It could be filled with fields. A disturbance here could travel there. Energy could move through space without needing a material substance like air or water to carry it. Radio waves, visible light, infrared radiation, and ultraviolet radiation are all disturbances of the same electromagnetic field. When you turn on a lamp, use a wireless signal, or feel warmth from sunlight, you are experiencing the behaviour of a field, not in an abstract classroom way, but in the ordinary practical life way where the kettle boils, the phone connects, and the lamp reveals that yes, the cat has knocked something over again. Then quantum theory arrived and made the field story even stranger, but also deeper. In quantum physics, energy is not always exchanged in smooth continuous amounts. Fields can be excited in discrete packets. For the electromagnetic field, those packets are photons. A photon is not a tiny hard bead of light in the everyday sense. It is a quantum of excitation in the electromagnetic field. That word excitation is important. It means the field has been stirred into a state that carries a definite amount of energy and other properties. When that excitation is absorbed by an atom, the atom changes. When it is emitted, light is produced. The particle is the way the field shows up when measured in a quantum way. Once physicists understood this, the idea expanded. If the electromagnetic field has photons as its quanta, perhaps other particles are also quanta of their own fields. This is the foundation of quantum field theory. There is an electron field. Every electron in the universe is an excitation of that same electron field. There are quark fields. Quarks are excitations of those fields. There are fields associated with particles that carry forces. There is also the Higgs field, whose excitation is the Higgs boson. This means that particles of the same type are not separate little manufactured units made in different cosmic factories. Every electron is a ripple of the same underlying electron field. Every Higgs boson is a ripple of the same underlying Higgs field. That idea helps explain something that might otherwise seem almost magical. All electrons are identical, not just similar, not just produced to a very high standard by nature's quality control department, but truly identical in their basic properties. One electron is not slightly more electronish than another. It does not have a tiny scratch, a personal history, or a preferred brand of tea. Electrons have the same mass, the same electric charge, and the same quantum properties wherever they appear. In a field picture, this makes sense. They are not individual handcrafted objects. They are excitations of one universal field. The sameness comes from the sameness of the field itself. This is very different from familiar objects. Two apples may look alike, but they are never perfectly identical. One is a little heavier, one is a little sweeter, one has a bruise that someone has turned away from in the fruit bowl and hoped nobody would mention. Everyday objects are made from enormous numbers of atoms arranged in complicated ways. Their differences come from their histories and structures. Fundamental particles, as far as we know, do not have that kind of internal variation. They are not built from a unique arrangement of smaller pieces. They are field excitations with fixed properties determined by the underlying theory. The word particle can therefore be a little misleading. It is useful, but it carries baggage. It invites us to imagine tiny pellets flying around. Sometimes that picture works well enough for rough thinking, especially in particle detectors where tracks and collision products are measured. But if we push the picture too far, it breaks. Quantum particles can behave like waves. They can interfere with themselves. They can be created and destroyed in interactions. Their number does not always stay fixed. A particle is not simply a miniature object that persists forever unless smashed. It is a quantum state of a field, and quantum fields can exchange energy in ways that allow particles to appear, disappear, transform, and scatter. This is why particle colliders are not simply microscopes in the ordinary sense. A microscope lets you look at something that is already there by using light or another probe. A collider does something more active. It concentrates energy into a tiny region and allows fields to respond. When protons collide at very high speeds, the energy of the collision can become new excitations of fields. New particles can be produced. Some of these particles are unstable and decay almost immediately into others. Detectors then record the results, and physicists work backward to infer what happened. It is not like cracking open a proton and finding a Higgs boson tucked inside. It is more like striking the vacuum and the fields hard enough that certain brief notes can be heard. This is a helpful way to think about the Higgs boson later. The Higgs boson is not stored inside ordinary matter waiting to be released. It is produced when enough energy is available to excite the Higgs field. The field is always present, but the boson is not always present as an actual particle. This is not unusual. The electromagnetic field is always part of the world too, but a particular photon exists only when the field is excited in that way. The electron field exists everywhere, but electrons appear where the field has electron excitations. The field is the underlying entity, the particle is the event, the disturbance, the measurable packet. Quantum field theory also changes how we think about forces. In older physics, one object pulls or pushes another across space. The Earth pulls the Moon. A magnet pulls a paperclip. A charged object attracts or repels another charged object. That is still a useful way to describe many situations, but in quantum field theory, interactions are described through fields and the exchange of quanta. Electrically charged particles interact through the electromagnetic field. The weak nuclear force involves its own force carriers. The strong nuclear force involves gluons, which are excitations of the gluon fields. This is not a picture of tiny messenger balls being tossed in a literal mechanical way, though that image is sometimes used. The real theory is more subtle, but the key point is that fields are not passive backgrounds, they are active participants. In the standard model of particle physics, every known elementary particle belongs to this field-based description. Matter particles such as electrons and quarks are excitations of matter fields. Force-carrying particles are excitations of force fields. The Higgs boson is the excitation of the Higgs field. The standard model does not say that the universe is made from particles first and fields second. It says that fields are fundamental, and particles are how those fields show themselves in specific circumstances. That is one reason the Higgs boson is so often misunderstood. People hear the word boson and think of a thing. But the deeper story is the Higgs field, because the boson is only the field made briefly visible through excitation and decay. Now the word boson itself also deserves a calm explanation. Particles in quantum physics fall into broad categories, depending on how they behave when grouped together. Matter particles such as electrons and quarks belong to one category called fermions. Force-carrying particles such as photons and gluons belong to another category called bosons. The Higgs boson is also a boson, but it is unusual because it is associated with a scalar field. That means it does not have spin in the way many other particles do. We do not need to dwell on spin in detail here, especially since the word already sounds more like something happening in a washing machine than in the foundations of reality. The important point is that the Higgs is not just another force carrier like the photon. It plays a different role, connected to the mechanism that gives many elementary particles their mass. This field-first view also helps explain why the Higgs field can be everywhere, without creating friction in the everyday sense. People often imagine particles moving through the Higgs field as though they are moving through syrup. That analogy can be useful for a moment, because it suggests that interacting with the field affects how particles behave, but it can also mislead. If space were filled with syrup, particles would slow down, lose energy, and eventually come to a sticky and undignified halt. That is not what the Higgs field does. The Higgs field does not act like a material fluid resisting motion. It changes the relationship between a particle's energy, momentum, and mass. It is built into the particle's basic behavior rather than acting as an ordinary drag force. A better way, though still only an analogy, is to imagine that fields set the rules for what kinds of excitations are possible. The electron field has excitations with the properties of electrons. The photon field has excitations with the properties of photons. The Higgs field contributes to the structure that allows certain particles to have mass. It is not slowing them as they move. It is part of what makes them the sort of particles they are. The difference is important. A particle with mass is not one that has been burdened by a sticky coating. It is one whose field and interactions make it behave as a massive particle. This can feel unsettling because it removes the little object from the centre of the story. Our instincts want the particle to be the real thing, and the field to be a mathematical description around it. But modern physics often reverses that instinct. The field is the real thing in the theory. The particle is a particular state of the field. If that feels upside down, it is only because daily life trains us differently. In daily life, you meet chairs, cups, doors, and people, not fundamental fields. No one has ever stubbed a toe on the electron field directly, though one could argue that all toe stubbing is ultimately a complicated electromagnetic interaction, which is not very comforting at the moment it happens. One of the great strengths of quantum field theory is that it can describe both matter and radiation in a unified way. It handles the creation and destruction of particles, something ordinary quantum mechanics by itself cannot do as naturally. This is essential for high-energy physics. In particle collisions, particles transform into other particles. Energy becomes mass. Mass becomes energy. Fields exchange excitations. The number and type of particles after a collision can differ from those before it. If we tried to describe all of this using only little permanent beads, we would struggle. Fields make the transformations natural. Consider what happens when an unstable particle decays. It does not contain the decay products in the way a box contains marbles. A Higgs boson, for example, can decay into different sets of particles depending on the probabilities allowed by the underlying fields and interactions. It is not choosing from a tiny internal menu taped to the inside of itself. It is a quantum excitation that couples to other fields, and those couplings determine the possible outcomes. When the Higgs boson decays, the energy and quantum properties of the Higgs excitation are transferred into excitations of other fields. That is the field language of particle decay. This matters for the question of what the Higgs boson is made of. If we imagine a particle as a little container, we ask what is inside it. But if a particle is an excitation of a field, the question changes. We ask what field is being excited. We ask whether that field is fundamental or composite. We ask how it interacts with other fields. We ask whether the excitation has internal structure that experiments can reveal. So far, the Higgs boson behaves like an elementary excitation of the Higgs field. No smaller parts have been detected. It is not known to be made of quarks, electrons, or anything else. It is, in the standard model, a fundamental ripple of a fundamental field. The phrase, as far as we know, is doing important work there. Physics is not a set of final declarations carved into stone and then dusted once a year. It is an experimental science. The standard model is incredibly successful, but physicists keep testing it because any tiny mismatch could reveal new layers. The Higgs boson might be exactly elementary, or it might turn out at higher energies or greater precision to have a deeper structure. Some theories imagine the Higgs as composite, made from more fundamental dynamics not yet observed. Others suggest additional Higgs fields or related particles. These ideas are not confirmed, but they exist because the Higgs sits in a place where known physics feels both complete and incomplete at the same time. Fields also help us understand why discovering the Higgs boson was not just adding one more particle to a list. It was confirming the existence of the Higgs field in a direct and dramatic way. Before the discovery, the Higgs field was already deeply woven into the standard model. It helped explain how particles associated with the weak force could have mass while the photon remained massless. It helped preserve the mathematical consistency of the theory. But until the Higgs boson was observed, the field's particle excitation had not been confirmed. Finding the boson was like finding the ripple that proved the invisible pond was there, although in this case the pond is spread through the entire universe, and the ripple vanishes almost as soon as it forms, which makes it a rather inconvenient pond for anyone hoping for a peaceful afternoon. The detectors at the Large Hadron Collider did not see the Higgs field directly. They saw patterns in collision debris. They saw excesses in particular decay channels. They saw statistical evidence accumulating until the result became strong enough to call a discovery. That is how much of modern particle physics works. It is not a matter of looking through a lens and spotting a tiny dot labelled Higgs. It is a matter of producing many collisions, recording enormous amounts of data, comparing that data to predictions, and finding the signature of a field excitation that lived for an unimaginably short time. The work is careful, patient, and deeply technical. It is also a reminder that the universe does not always reveal itself in ways suited to human eyesight. The field picture also brings a surprising kind of unity. The electron in your body and an electron in a distant galaxy are excitations of the same electron field. A photon from a lamp and a photon from a star are excitations of the same electromagnetic field. The Higgs field that gives mass to elementary particles here is the same Higgs field that fills space elsewhere. The universe is not assembled from separate local batches of ingredients. It is threaded through by universal fields. The particles are local appearances of those fields, but the fields themselves belong to the whole structure. That does not mean all fields behave the same way. The electromagnetic field can have waves that travel freely across space. The electron field has excitations that carry electric charge and have mass. Quark fields are bound up with a strong force in ways that prevent isolated quarks from being seen on their own under ordinary conditions. The Higgs field is different again because of its non-zero vacuum value and its role in mass generation. Each field has its own rules, its own allowed excitations, and its own way of interacting. The Standard Model is, in a sense, a catalogue of these fields and their relationships. It is worth pausing on how odd and elegant that is. The world feels solid. A table resists your hand. A wall does not let you pass through it, which is useful for architecture and disappointing for anyone attempting superhero behaviour. But the solidity of matter is not the result of tiny hard balls pressing against each other like packed marbles. It arises mostly from electromagnetic interactions, quantum rules, and the structure of atoms. The particles themselves are field excitations. The space between and within them is filled with fields. The everyday firmness of the world is an emergent result of deeper field behaviour. Reality is stable enough to hold a teacup, but underneath, it is not built the way our senses first suggest. The Higgs field is part of that hidden stability. It helps set the masses of fundamental particles, and those masses help determine the structure of atoms and the behaviour of matter. If the electron mass were very different, chemistry would change. If quark masses were different, atomic nuclei might not work as they do. The universe is sensitive to the properties of its fields. This is why physicists care so much about measuring the Higgs boson carefully. Its properties tell us about the field, and the field tells us about the basic conditions that make our kind of universe possible. Still, we should not turn the Higgs field into a magical explanation for everything. It does not account for all mass in the everyday world. Much of the mass of protons and neutrons comes from the energy of the strong force and the motion and interactions of quarks and gluons inside them. The Higgs field gives mass to quarks themselves, but the mass of ordinary matter is mostly produced by the dynamics of the strong interaction. This is one of those details that keeps the story honest. The Higgs is essential, but it is not the whole mass story. Physics is rarely a single actor play. It is more often an ensemble cast, and some of the cast members are very small, very noisy, and impossible to invite to dinner. By now, the phrase "before particles," there were fields, should feel less like a slogan and more like a shift in viewpoint. We are not saying that fields existed in time before particles in the ordinary historical sense, as though the fields arrived early and set up chairs before the particles came in late carrying snacks. We are saying that in the structure of the theory, fields are the deeper ingredients. Particles are excitations of fields. To understand a particle properly, especially one like the Higgs boson, we have to understand the field it belongs to. This shift prepares us for the next part of the Higgs story. If all known particles are excitations of fields, then what makes the Higgs field so special? Why does this field have a background value even in empty space? How does that quiet presence affect other particles without acting like ordinary friction? Why did physicists need it in the first place? And why did finding its boson matter so much? These questions take us from the general idea of fields to the particular field that changed our understanding of mass. The Higgs field is not loud. It does not shine. It does not push on you in any obvious everyday way, but it is everywhere, and through its interactions it helps give the universe the familiar structure we live inside. So from the broad field-filled landscape of modern physics, we can move closer now to that quiet, invisible background, the one whose small ripple became one of the most celebrated discoveries in science. So let us stay with the field idea a little longer, because this is where the Higgs story becomes both clearer and stranger. We have moved away from the old picture of particles as tiny solid beads, and we are now standing in the quieter landscape of modern physics, where fields are the deeper ingredients and particles are the brief local excitations those fields can produce. That shift matters more for the Higgs field than perhaps for any other field in the Standard Model, because the Higgs field does not simply wait to be disturbed. It is already doing something unusual before any particle appears. It has a constant presence throughout space, even in what we would normally call empty space, and that constant presence helps determine why many elementary particles have mass at all. That can sound a little too grand at first, so it is worth approaching carefully. The Higgs field is not an ocean in the ordinary sense. It does not slosh around planets. It does not make waves you could surf on, although if it did, one suspects the safety briefing would be quite serious. It is not made of water, atoms, dust, or any familiar material. When people compare it to an ocean, they are reaching for a way to describe something that fills all of space and can have ripples. The field is the everywhere part. The Higgs boson is the ripple part. But the analogy has limits, and good physics often begins by knowing where an analogy stops. The Higgs field is not a substance spread through space. It is a physical field with a value everywhere, and that value affects how other fields behave. The most important feature of the Higgs field is that its lowest energy state is not empty in the simple way we might expect. For many fields, we imagine the quietest state as a kind of stillness with no field value. The electromagnetic field, for example, can be in a state with no electromagnetic wave passing through a region. But the Higgs field is different. Even when it is in its quietest possible state, it still has a background value. Empty space contains this Higgs field value everywhere. It is not caused by matter. It is not stronger near your chair and weaker near the window. As far as we know, it is spread uniformly through the universe. That is one of the reasons it is so important. It is part of the background condition of reality. This background value is often the part that makes people pause. If empty space has a Higgs field value, then empty space is not a blank nothing. It has a built-in structure. It has a condition that particles respond to. You are not moving through a material fluid when you cross a room, but the particles in your body are part of a world where the Higgs field is already present. The electron field, the quark fields, and other fields interact with it in specific ways. Those interactions are connected to the masses of the particles we observe. Without that background Higgs field value, the particles of the Standard Model would not have the same masses, and the universe would not have the same chemistry, atoms, stars, planets, or sleepy conversations about physics. A common way to explain this is to say that particles get mass by moving through the Higgs field. That is a useful first sentence, but it can lead the imagination in the wrong direction if we are not careful. It can make the Higgs field sound like thick syrup, and particles like tiny spoons pushing through it, but mass is not ordinary drag. A particle with mass is not simply one that is being slowed down by an invisible goo. If the Higgs field acted like syrup, particles would lose energy as they moved, and the universe would behave very differently. The Higgs field is not resisting motion in that everyday sense. Instead, it changes the fundamental relationship between a particle and the way it carries energy and momentum. It helps define what kind of particle that excitation is. That may feel less intuitive, but it is closer to the truth. In quantum field theory, a particle is an excitation of a field. The properties of that excitation depend on the rules of the field and on how it interacts with other fields. When a particle field interacts with the Higgs field, its excitations can behave as massive particles. The interaction is not an accidental coating added later. It is woven into the particle's identity. An electron has the mass it has because of how the electron field couples to the Higgs field. A top quark has a much larger mass because its field couples more strongly. A photon remains massless because it does not acquire mass through the Higgs field in the same way. This is not a matter of size. It is not that the top quark is a bigger lump in the ordinary sense. It is about interaction strength. This is one of the more surprising lessons of particle physics. Mass at the elementary level is not simply the amount of stuff inside a particle. An electron, as far as we can tell, has no smaller parts. It is not a little container filled with mass grains, yet it has mass. The Higgs field helps explain how that can be true. Mass can be a property that arises from a field's relationship with the Higgs field. This is why the Higgs field is so central. It allows elementary particles to have mass without needing to be made of smaller ingredients. To see why physicists needed such an idea, we have to remember that the Standard Model is built on symmetries. Symmetry in physics is not only about pretty shapes, though pretty shapes are welcome when they appear. Asymmetry is a kind of rule that says the laws of physics stay consistent under certain changes. These symmetries are deeply important because they guide what kinds of particles and interactions can exist. The electroweak theory, which unifies the electromagnetic force with the weak nuclear force at high energies, had a beautiful mathematical structure. But there was a problem. The particles that carry the weak force needed to be massive, because the weak force acts over extremely short distances. The photon, which carries electromagnetism, needed to remain massless. Simply inserting masses by hand would break the symmetry and damage the theory. The Higgs field solved this problem in an elegant way. It allowed the underlying theory to keep its symmetry at a deeper level, while the world we observe looks as though that symmetry has been hidden or broken. This is called spontaneous symmetry breaking, although the phrase sounds more dramatic than the idea needs to feel. A simple, everyday comparison is a round table at dinner with napkins placed evenly around it. The table arrangement may be symmetrical, but once someone chooses a seat, the symmetry of the situation is no longer obvious. The underlying setup allowed all seats equally, but the actual outcome picked one. The Higgs field does something somewhat similar in a much more precise and mathematical way. The underlying rules have a symmetry, but the Higgs field settles into a particular non-zero value throughout space, and that changes how particles behave. This settled value of the Higgs field is often described as the Higgs field's vacuum value. It is the value the field has in empty space at its lowest energy. The word vacuum can again be misleading, because this vacuum is not nothing. It is the state of the fields when no actual particles are present. The Higgs field, even in that state, has this ever-present value. That is why the field can affect particles everywhere. It is not something particles have to search for. They do not travel until they encounter a patch of Higgs field like someone wandering into fog. They're always in it, because it is part of space itself. This also helps explain why the Higgs field does not have a preferred direction in ordinary space. It is not blowing from left to right. It is not stronger north than south. It does not make the universe feel like it is moving through a cosmic wind. If it did, experiments would notice that particles behave differently depending on direction, and we would have a rather awkward problem to discuss over breakfast. Instead, the Higgs field is the same in every direction and at every location, as far as we can measure. This uniformity is one reason it can shape particle masses without ruining the basic symmetry of space itself. It is everywhere, but it does not point anywhere. The Higgs field is also different from a force field in the familiar sense. It is not pulling particles together like gravity, or pushing charged particles like electromagnetism. You do not feel a Higgs force tugging on your hand. The Higgs field works more quietly. Its presence changes the allowed behavior of other fields. It gives certain particles their rest mass, meaning the mass associated with their existence even when they are not moving. That phrase, rest mass, can sound strange in a universe where quantum particles are not little billiard balls sitting still, but the basic idea is that some particles have mass as an intrinsic property. The Higgs field helps provide that property. The particles most directly affected by the Higgs field include quarks, charged leptons such as electrons, and the massive carriers of the weak force. Different particles interact with the Higgs field differently, which is why their masses vary so wildly. The electron is light. The top quark is extremely heavy by elementary particle standards. The weak force carriers are massive. Neutrinos have very tiny masses, though their exact connection to the Higgs field is still a deeper and not fully settled story. The pattern of particle masses is one of the great mysteries that remains. The Higgs field explains how particles can have mass, but it does not fully explain why each particle has exactly the mass it does. That distinction is important. The Higgs mechanism is not a complete answer to every mass question. It gives the framework. It tells us that masses arise from interactions with the Higgs field, but the strengths of those interactions are put into the standard model as numbers measured from experiment. We do not yet have a deeper explanation for why the electron couples to the Higgs field with one strength and the top quark with another. It is a little like having a very good piano and knowing exactly how each key produces sound, but still not knowing why the song written for it has this particular melody. The mechanism works, the pattern remains mysterious. This is one reason physicists continue studying the Higgs field even after the Higgs boson was discovered. The discovery confirmed that the field exists in the way the theory predicted, but it did not close the subject. It opened a new era of measurement. How strongly does the Higgs boson interact with other particles? Does it behave exactly as the standard model says? Does it interact with itself in the predicted way? Are there additional Higgs-like particles? Is the Higgs field connected to dark matter? Could it have played a role in the early universe? Each of these questions points beyond the simple headline. Finding the Higgs boson was not the end of the Higgs story. It was more like finally opening a door and discovering that the hallway continues. The self-interaction of the Higgs field is especially important because it tells us about the shape of the field's energy landscape. That phrase may sound abstract, but it describes a very real question. Why does the Higgs field settle into the value it has? What is the structure of the potential that makes this value the lowest energy state? Physicists want to measure how the Higgs field interacts with itself, because that can reveal whether the standard model picture is complete. To do that, they look for rare events where pairs of Higgs bosons are produced. These events are very difficult to detect because they happen rarely and leave complicated patterns. It is a bit like trying to hear two extremely brief whispers during a fireworks display, while everyone nearby is also discussing lunch. But the effort matters because it probes the deeper nature of the field. The Higgs field may also be connected to the history of the early universe. In the very hot, dense conditions shortly after the Big Bang, the Higgs field may not have had the same settled value it has today. At extremely high temperatures, the symmetries of the electroweak theory may have been restored, meaning particles that now have mass through the Higgs field would have behaved differently. As the universe expanded and cooled, the Higgs field settled into its present value. This change is called the electroweak phase transition. It is not quite the same as water freezing or steam condensing, but it is distant cousin in the sense that the state of a system changes as conditions change. The details of that transition might even connect to why the universe contains more matter than antimatter, though the standard model by itself does not seem to provide the full answer. That is another reason the Higgs field feels like a quiet ocean beneath reality. It is not only involved in particle masses now, it may also have helped shape the evolution of the universe when it was young. Its present value is part of why atoms and structures can exist today. Its past behaviour may hold clues about how the universe became the kind of place where matter survived in abundance. We should be cautious here, because many of these ideas remain under investigation. But the possibility is fascinating. The Higgs field is not merely a modern laboratory curiosity. It may be woven into the cosmic story from the earliest moments onward. There is also the question of stability. Measurements of the Higgs boson and the top quark suggest that our vacuum may be in a delicate situation, perhaps stable, perhaps metastable, depending on precise values and unknown physics at higher energies. Metastable means that the vacuum could be long-lived even if it is not the deepest possible state. This sounds alarming if phrased carelessly, but there is no practical reason to worry. The universe has lasted for billions of years, and any hypothetical change would be fantastically unlikely under present conditions. Still, for physicists, this is a profound clue. The Higgs field may be telling us something about the ultimate structure of physical law. Why is its value what it is? Why is its mass what it is? Why does the vacuum appear to sit near the boundary between different possibilities? These are not questions answered by discovering the boson alone. The Higgs boson itself is the way we experimentally access the field. When high-energy collisions excite the Higgs field, a Higgs boson can appear. It is heavy and unstable, so it decays almost immediately into other particles. By studying those decay patterns, physicists test whether the Higgs field couples to particles as expected. The results so far match the Standard Model impressively well. The Higgs boson decays into particle pairs in ways consistent with the idea that stronger coupling to the Higgs field corresponds to greater mass. That is a beautiful confirmation, but physicists are not finished. They are looking for small deviations, the tiny cracks where new physics may shine through. It is useful here to keep the relationship between field and boson clear. The Higgs field is not made of Higgs bosons in the same way a beach is made of grains of sand. The field is the underlying entity. Higgs bosons are excitations of it. When no Higgs bosons are present, the Higgs field still exists. This can feel backwards, because we are used to thinking of a field as something made by particles. For example, in simple school explanations, electric fields are created by electric charges. But in quantum field theory, fields are primary. Particles are the excitations. The Higgs field is not a crowd of Higgs bosons. It is the field whose ripple is a Higgs boson. This point is important for the question of what the Higgs boson is really made of. The Higgs boson is made of a disturbance of the Higgs field, if we allow made of to stretch beyond its everyday meaning. It is not known to contain smaller particles. It is not a composite of quarks or leptons. In the Standard Model it is elementary. But because the Higgs field itself is so unusual, many physicists suspect it may be connected to deeper layers. The field might be fundamental, or it might emerge from something more basic. The boson might be point-like at the scales we have tested, or it might reveal structure at scales we have not reached. At present, the evidence supports the simplest Standard Model picture, but the question remains alive. The quietness of the Higgs field is part of what makes it difficult to appreciate. It does not announce itself in daily life. You do not wake up and feel the Higgs field making your electrons massive. You feel the weight of your body because of gravity acting on the mass energy of the matter you are made of. You feel the floor because electromagnetic forces stop atoms from passing through atoms. The Higgs field is further down in the explanation, shaping some of the properties that allow matter to behave as it does. It is not a sensation. It is a condition. It is not loud, but it is foundational. A nice way to think about it is to compare it with grammar. When you hear a sentence, you usually notice the words and the meaning. You may not notice the grammar unless something goes wrong. Yet grammar quietly shapes how the words fit together. It is not the message itself, but it helps make the message possible. The Higgs field is not the whole universe. It is not matter, light, gravity, or time, but it is part of the grammar of particles. It helps determine which particles are massive, which interactions work as they do, and how the electroweak theory becomes the world we observe. Still, grammar is only an analogy, and the Higgs field is more than an organizing idea. It is a physical field with measurable consequences. The discovery of the Higgs boson confirmed that the field can be excited. The measured properties of that boson continue to test the field's role. If the Higgs boson had not been found, the Standard Model would have faced a serious crisis. Something else would have had to explain particle masses and preserve the consistency of the theory. Instead, the boson appeared where expected, with properties close to expectation, and the Higgs field took its place as one of the central features of modern physics. The simplicity of the field is almost suspicious. A single scalar field spread everywhere, with a non-zero vacuum value, giving mass to fundamental particles through interactions. It is elegant, but it also raises questions. Why this field? Why this value? Why this mass? Why one Higgs boson and not a larger family? Nature may be simple here, or it may be hiding complexity behind a simple face. Physicists are patient with such things because nature has done this before. Atoms once looked elementary. Protons once looked elementary. Even the vacuum once looked empty. Each time, closer inspection revealed more structure. The Higgs may or may not follow that pattern. For now, what we can say is that the Higgs field is the quiet background that makes the Higgs boson meaningful. Without the field, the boson would not exist. Without the field's vacuum value, the mass structure of the standard model would be radically different. Without the ability to excite the field, we would not have had the experimental confirmation that arrived at the Large Hadron Collider. The field is not a decorative addition to reality. It is part of the reason reality has the particle properties it does. So the Higgs field sits beneath the visible world in a very specific scientific sense. It is not beneath as in below your feet, and it is not beneath as in a hidden layer of matter under the floorboards. It is beneath as in more fundamental to the explanation. The objects around you are made of atoms. Atoms are made of electrons and nuclei. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons. The properties of quarks and electrons are shaped partly by their interactions with the Higgs field. The field is not visible, but its consequences are everywhere. It is one of the quiet reasons why the world has form. And once we understand that, the Higgs boson itself becomes less like a mysterious object and more like a message from the field. It is a temporary ripple produced when enough energy disturbs the Higgs field. It appears, decays, and leaves clues behind. Those clues tell physicists that the field is real and that its interactions match the pattern required by the standard model. The boson is famous because it is detectable. The field is important because it is always there. From this quiet field we can now move toward the ripple itself. If the Higgs field is present everywhere, what exactly happens when a Higgs boson is produced? How can a field become a particle? Why does the boson vanish so quickly? What do detectors actually see if they never see the Higgs boson directly? The next step is to follow that brief disturbance, from the calm background of the field into the violent little moment of a particle collision, where the invisible field speaks for less than a blink, and then disappears into the particles we can measure. To follow the Higgs boson properly, we have to begin with a slightly awkward fact. No one has ever seen one in the ordinary sense. There is no photograph of a Higgs boson. There is no tiny glowing dot on a screen where a scientist points and says, "There it is," looking rather pleased with itself. The Higgs boson does not sit still, does not travel through a detector leaving a neat little trail, and does not wait around long enough to be admired. It appears for an incredibly brief moment, and then disappears into other particles. So when physicists say they discovered it, they do not mean they caught it like a firefly in a jar. They mean they found its fingerprints, its echoes, its after effects, written into the debris of high-energy collisions. That sounds indirect, but indirect evidence is often how physics works at the smallest scales. If you hear a crash in the kitchen and find a broken cup, a guilty-looking cat, and no other reasonable suspect, you do not need to have watched the cup fall to understand what happened. Particle physics is rather like that, except the cup is smaller than an atom, the cat is a quantum field, and the kitchen costs several $billion to build. The Higgs boson is known through the particles it becomes, through the patterns it leaves behind, and through the careful agreement between those patterns and the predictions of the Higgs field. A Higgs boson is a ripple in the Higgs field. That is the simplest useful sentence, but it deserves to be unpacked slowly. The Higgs field is present everywhere, even in empty space. Most of the time it sits in its quiet background state. It is not producing Higgs bosons everywhere around you. It is not fizzing with little Higgs particles in your room like invisible dust. It is simply there, as part of the vacuum. A Higgs boson appears when that field is given enough energy in the right way to become excited. The field lifts, so to speak, into a concentrated quantum disturbance. That disturbance is what we call the Higgs boson. This is similar in spirit to the way a photon is a quantum of the electromagnetic field. When the electromagnetic field is excited in a certain way, we can get light. When the Higgs field is excited in a certain way, we can get a Higgs boson. But the Higgs boson is much harder to produce than an ordinary photon. You create photons all the time. Turn on a lamp, warm your hands near a fire, glance at a screen, and photons are everywhere doing their little errands at light speed. The Higgs boson, by contrast, is heavy, unstable, and reluctant to appear unless the conditions are extreme. It is not the sort of particle one finds casually drifting through the living room, unless your living room has been built suspiciously close to a particle collider, in which case there may be other concerns. To create a Higgs boson, physicists need to concentrate enormous energy into a very tiny region. This is what happens at the Large Hadron Collider, a vast circular machine beneath the border of Switzerland and France. It accelerates protons to very high speeds and sends them crashing into one another. The protons themselves are not simple little balls. They are messy bundles of quarks, gluons, and energy held together by the strong force. When two protons collide at such high energies, their internal ingredients can interact violently. For a tiny moment, the energy in the collision can excite fields that are normally quiet. If the conditions are right, one of those excitations can be a Higgs boson. It is worth remembering that this does not mean the Higgs boson was hiding inside the proton. That is a common misunderstanding. A proton is not a little box that contains a Higgs boson, waiting to be shaken loose like a coin from an old sofa. The Higgs boson is created from the energy of the collision. In modern physics, energy can be transformed into particle excitations, as long as the rules of conservation are obeyed. A high-energy collision is like striking the fabric of fields hard enough to make rare notes ring out. Most of the time, many other particles are produced. Very rarely the Higgs field is excited in just the right way, and the Higgs boson appears. But then it is gone almost immediately. The Higgs boson has an extraordinarily short lifetime. It is so unstable that it decays before it can travel any measurable distance in a detector. This is why physicists never observe a Higgs boson track directly. Many particles leave trails because they move through detector material, interact with it, and produce measurable signals. The Higgs boson does not have that kind of patience. It forms and decays almost at once into other particles. Those particles, or the particles they themselves decay into, are what detectors actually record. This decay is not a sign that the Higgs boson was made of those particles beforehand. That point is subtle but important. When a Higgs boson decays into two photons, for example, it does not mean it had two photons tucked inside it. When it decays into other particles, it does not mean those were its ingredients in the ordinary sense. Decay in quantum field theory is a transformation of energy and quantum properties from one field excitation into others. The Higgs excitation couples to other fields, and those couplings allow it to become different combinations of particles. It is less like breaking a toy apart to see what pieces were inside, and more like a musical note fading into other notes because the instrument and the room allow that resonance. That may feel odd because in daily life, when something breaks apart, its pieces usually existed inside it already. A biscuit broken in half contained those halves before you snapped it, even if you were trying to be polite and take the smaller piece, a noble effort that fools no one. But particles are not biscuits. An unstable particle decay is not just a hidden object coming apart, it is a quantum process where one state changes into other possible states. The final particles are real, but they are not necessarily pre-existing parts. They are produced in the decay. The Higgs boson can decay in several ways. Some are more common, some are rarer, and some are easier for detectors to identify than others. It can decay into pairs of heavy particles when those paths are available through quantum processes. It can decay into photons, even though photons themselves do not get mass from the Higgs field, because the decay can happen through intermediate interactions involving other charged particles. It can decay into particles related to the weak force, or into heavier matter particles such as bottom quarks. Each possible decay route tells physicists something about how the Higgs field couples to other fields. This is why the discovery required enormous amounts of data. The Higgs boson is not produced in every collision, far from it. Most collisions at the Large Hadron Collider produce more ordinary particle sprays. Even when a Higgs boson is produced, its decay products can resemble those from other processes. Physicists must separate a small signal from a very large background. This is a little like trying to hear one person whisper your name in a crowded station while several thousand people are dragging suitcases over tiled floors. The whisper may be there, but you need patience, statistics, and excellent noise reduction. The detectors built for this task are enormous, intricate instruments surrounding the collision points. They are layered like scientific onions, although onions are rarely chilled, wired, and asked to detect muons. Different layers measure different kinds of particles. Some track charged particles as they curve through magnetic fields. Some measure the energy of photons and electrons. Others measure the energy of particles made of quarks and gluons. The outer systems detect muons, heavier cousins of electrons that can pass through much of the detector. By combining all this information, physicists reconstruct what happened in the collision. The Higgs boson is inferred when the reconstructed final particles show a pattern consistent with a parent particle of a particular mass and behaviour. One of the cleanest discovery routes involved two photons. The Higgs boson could decay into two high-energy photons, and by measuring those photons very precisely, physicists could reconstruct the mass of the particle that produced them. There were many ordinary events that also produced photon pairs, but when enough data accumulated, a small excess appeared at the mass expected for the Higgs. Another important route involved decay patterns connected to particles of the weak force, which then produced charged leptons and neutrinos. Different channels, different clues, all pointing toward the same new particle. The discovery was announced in 2012 by the major experiments at the Large Hadron Collider. It was a remarkable moment, not because physicists had stumbled upon something completely unexpected, but because a long-predicted piece of the Standard Model had finally shown itself. The Higgs boson had been proposed decades earlier as the particle associated with the Higgs field. The theory had worked so well in other areas that many physicists expected something like it to exist. But expectation is not discovery. Nature is the final judge, and nature has a way of making even very confident scientists wait in line. When the data became strong enough, the discovery confirmed that the Higgs field was not just a convenient mathematical trick. Its particle excitation was real. That mattered enormously. The Standard Model required a mechanism to explain how certain elementary particles have mass, while preserving the structure of the electroweak theory. The Higgs field provided that mechanism. Finding the Higgs boson confirmed the field in the way only experiment can. It was like seeing a footprint in fresh snow, and knowing that the quiet animal you had predicted was actually there, though in this case the animal was a quantum field, and the snow was a mountain of collision data. Still, calling the Higgs boson a ripple can make it sound gentler than the conditions needed to produce it. The field itself may be quiet, but the collision environment is violent. Protons are accelerated to energies far beyond anything encountered in ordinary matter. When they collide, the energy density in that tiny region is extreme. Quantum fields respond according to the rules of particle physics. Gluons interact, quarks scatter, heavy particles appear, unstable states decay, and showers of particles burst outward into the detector. Somewhere in that chaos, rarely, The Higgs field is excited and a Higgs boson forms. Then it decays before the detector can meet it directly. There is a beautiful strangeness in that. The Higgs boson is famous, yet almost everything we know about it comes from its disappearance. It is defined by the field it belongs to, produced in rare collisions, and measured through what it becomes. It is not an object you can isolate and store. You cannot put Higgs bosons in a bottle for later use, which is probably fortunate, because someone would inevitably try to sell artisanal Higgs water at an alarming price. The Higgs boson belongs to a world where existence can be brief and still scientifically meaningful. The briefness does not make it less real. Many real things are temporary. A flash of lightning is brief. A note from a violin fades. A bubble appears and pops. We do not deny that these things existed because they did not last. In particle physics, duration is not the measure of importance. The Higgs boson lasts for an unimaginably short time, but during that time it carries specific properties. It has mass, no electric charge, and no spin. It interacts with other particles in ways predicted by the Higgs mechanism. It can be produced and it can decay. Those facts are enough to make it a real feature of the physical world. The fact that it has no spin is one of the things that makes it unusual. Most elementary particles have some kind of intrinsic angular momentum called spin, though this is not spin in the everyday sense of a tiny ball turning around. The Higgs boson is different. It is a scalar particle, meaning its field has a value that does not point in a spatial direction. This fits with the idea that the Higgs field can fill space uniformly without creating a preferred direction. If the Higgs field pointed somewhere, the universe might behave differently along that direction, and experiments would have noticed. The scalar nature of the Higgs is part of why it can do its quiet work without making space look lopsided. This also makes the Higgs boson unique in the known particle family. The standard model contains many matter particles and force-carrying particles, but the Higgs boson is the only confirmed elementary scalar particle. That uniqueness is one reason physicists watch it so closely. It may be exactly what the standard model says it is, a fundamental scalar excitation of the Higgs field. Or it may be the first visible sign of a richer sector of physics. There might be additional Higgs particles. The Higgs could be related to new symmetries. It could be composite at scales we have not yet reached. None of that has been confirmed, but the possibility keeps the Higgs from being merely a solved problem. Every measurement of the Higgs boson is therefore a test. How often is it produced? How often does it decay into different particles? Does it couple more strongly to heavier particles, as expected? Does it interact with itself? Does it have any unexpected decay modes? Does it show any sign of being larger than a point-like particle, or made of smaller constituents? So far, the answers have been reassuringly standard model-like. That is a triumph, but also a tease. The standard model works beautifully, and yet we know it cannot be the whole story because it leaves out gravity in quantum form, dark matter, and other deep mysteries. The Higgs boson sits there, behaving politely, while physicists look at it as if it might be hiding something behind its back. When we say the Higgs boson is a ripple in the invisible sea, we should remember that the sea is the field, not a collection of bosons. This is a common place for confusion. The Higgs field fills space. Higgs bosons are excitations of that field. In the same way, the electromagnetic field can exist without a particular photon being present. A calm field is still a field. A ripple is what happens when energy disturbs it. The universe around you is full of the Higgs field, but not full of actual Higgs bosons. The field is the steady background. The boson is the rare disturbance. The invisibility of the Higgs field also does not mean it is imaginary. Many real things are not directly visible. Air is invisible most of the time, yet it moves leaves, carries sound, and becomes very noticeable when absent. Magnetic fields are invisible, yet they guide compass needles. The Higgs field is more deeply hidden than these everyday examples, but the principle is similar. We know it by its effects. We know it because the theory that includes it predicts particle behavior with extraordinary success. We know it because its excitation was produced and measured. We know it because the masses and interactions of particles fit a pattern that would be very difficult to explain without it. There is also a subtle difference between detecting the Higgs boson and understanding what it is made of. Detection tells us that a particle with the expected properties exists. Understanding asks whether that particle is fundamental or composite, whether the field is elementary or emergent, whether deeper laws explain its mass and couplings. The discovery answered one question and sharpened many others. It told us the Higgs boson exists. It did not tell us why the Higgs field has the value it has. It did not tell us why particle masses follow their particular pattern. It did not tell us whether the Higgs is alone. The ripple picture gives us a way to hold these ideas without forcing them into ordinary object language. A ripple is not made of separate little ripple pieces. It is a pattern in something deeper. The Higgs boson is a pattern of excitation in the Higgs field. If the field is fundamental, then the boson is fundamental too as far as the standard model is concerned. If the field turns out to emerge from something deeper, then the boson may be a sign of that deeper structure. Experiments have not yet found such substructure, so the honest answer remains that the Higgs boson is, to our best knowledge, an elementary excitation. One of the reasons this answer feels strange is that it refuses the comfortable nesting box story. We want to say the Higgs boson is made of smaller things, and those smaller things are made of still smaller things. That story works for some objects. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. But not every question continues downward in the same way. At some point in our current theories, we reach fields that are not described as being made of smaller ingredients. The Higgs field is one of those. The boson is its excitation. The recipe is not a list of parts but a set of field rules, and this is where the Higgs boson becomes a useful teacher. It teaches us that reality is not always built like familiar matter. It teaches us that particles can be temporary expressions of fields. It teaches us that emptiness can have structure. It teaches us that mass is not merely stuff packed into stuff. It teaches us that the most important thing in a collision may be the particle that vanishes before anything can see it directly. The Higgs boson is less like a marble, and more like a brief word spoken by the Higgs field, and physicists have learned to read the echo. The detectors at the Large Hadron Collider are, in this sense, not only machines for finding particles, they are machines for listening to fields. They watch what happens when energy is poured into the vacuum at a tiny point. They record the shower of particles that emerges. They compare millions and billions of events. They ask whether the patterns match the known fields or hint at new ones. Most events are ordinary by particle physics standards, which still means wildly complicated by bedtime standards. A small number carry the signature of the Higgs. Fewer still may one day carry signs of something beyond it. The challenge now is precision. Discovery was the first great step. The next step is measuring the Higgs boson so carefully that even tiny deviations become visible. If the Higgs couples to some particle slightly differently than expected, that could be a clue. If it decays in a rare, unexpected way, that could be a clue. If pairs of Higgs bosons reveal a self-interaction that differs from the standard model prediction, that could be a clue. The Higgs boson may look simple, but simple things measured well can become doorways. A quiet ripple can reveal the shape of the whole sea. There is a calm satisfaction in knowing that the Higgs boson is not some mystical object buried inside matter, but a precise quantum excitation of a field. It removes some of the fog from the famous name. It also makes the story deeper. The Higgs boson is not important because it is a tiny piece from which everything is built. It is important because it confirms the existence of a field that changes the behavior of elementary particles throughout the universe. The boson is the sign, the field is the source, the ripple is brief, the sea remains. And once we have the Higgs boson in view this way, the original question returns with more force. If it is a ripple, then what is the ripple made of? If it is elementary, what does elementary really mean? Does saying it has no known smaller parts settle the matter, or merely describe the limit of our current experiments? Could the Higgs boson be composite in a way too small or too energetic for us to have detected? Could it be tied to hidden particles, unseen fields, or a deeper structure beneath the standard model? To answer that, we need to look directly at what physicists mean when they ask whether something is made of anything at all, and why the Higgs boson sits right at the border between a confirmed discovery and an open question. Now we can return to the question that has been quietly waiting underneath everything else. What is the Higgs boson really made of? It sounds like the sort of question that should have a tidy answer. A chair is made of wood, metal, fabric, and possibly one screw that was left over during assembly and now causes mild concern. A cloud is made of tiny droplets of water or crystals of ice. A human body is made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms contain electrons and nuclei, and nuclei contain protons and neutrons. If we keep going, surely the Higgs boson must also be made of something. That is the instinct. We follow the trail downward, opening smaller and smaller boxes, expecting to find one final hidden box at the bottom. But the Higgs boson does not behave like a box. As far as modern physics can tell, it does not contain smaller pieces. It is not made of quarks. It is not made of electrons. It is not made of photons. It is not made of little knots of ordinary matter. In the standard model, the Higgs boson is an elementary particle, which means it has no known internal structure. More carefully, it is the quantum excitation of the Higgs field. That is the honest answer, and it is both beautifully simple and deeply strange. The Higgs boson is made of a ripple in the Higgs field, if we allow the phrase made of to stretch beyond its everyday meaning. It is not made from material ingredients, it is made from field excitation. This is where language begins to struggle a little. The words made of were built for ordinary objects. They are comfortable in kitchens, workshops, gardens, and factories. They know what to do with bread, bricks, wool, and clay. They become less confident when invited into quantum field theory. A field excitation is not like flour in a cake. It is not a substance packed inside a shell. It is an event in a field, a localized carrying of energy and quantum properties. When the Higgs field is excited in the right way, that excitation behaves as a Higgs boson. It has measurable properties. It has a mass. It has no electric charge. It has no spin. It is unstable and decays rapidly. But it is not a tiny object with parts hidden inside. Think again of a wave, but gently, because this analogy can help only so far. If you see a wave moving across a pond, you might ask what the wave is made of. The answer is not that the wave is made of some special wave substance. The wave is a pattern of motion in the water. It is the water behaving in a particular way. You can measure the wave. It can carry energy. It can move across the surface. It can disturb a leaf or rock, a floating twig. It is real, but it is not separate from the medium. The Higgs boson is something like that, except the medium is not water. It is the Higgs field, and the ripple is not continuous in the everyday sense. It is quantized, meaning nature allows the field to be excited in packets. A Higgs boson is one such packet. Of course, the Higgs field itself is not made of water or anything like water. It is not a hidden fluid. It is not thick, wet, sticky, or waiting to splash anyone who moves too quickly through the universe. The wave image is only a doorway. It helps us stop picturing the Higgs boson as a little bead. Once we have stepped through that doorway, we have to let the deeper field picture take over. A quantum field is a fundamental feature of the theory. It exists throughout space. Its excitations are particles. The Higgs field is one of those fields. The Higgs boson is the particle that appears when that field is excited. So when someone asks what the Higgs boson is made of, a physicist might answer, in our current best theory, nothing smaller. Not because it is nothing, but because it is not composite. Composite means built from parts. A proton is composite. It contains quarks and gluons bound together by the strong force. A neutron is composite. An atom is composite. A molecule is composite. But an electron is not known to be composite. A photon is not known to be composite. A quark is not known to be composite. And the Higgs boson so far is not known to be composite either. It appears to be elementary. That word elementary should be handled with care. It does not mean absolutely proven to be indivisible forever and ever, with a certificate signed by the universe. Science rarely speaks that way. It means that experiments have found no evidence of smaller structure. When physicists probe particles at higher and higher energies, they are testing whether those particles behave like point-like excitations, or whether they show signs of internal parts. If a particle had substructure, collisions might reveal unexpected patterns, the way scattering experiments once revealed that atoms had nuclei, and later that protons had internal components. So far, the Higgs boson behaves like a point-like elementary particle within the limits of what we can measure. This is not a small achievement. The Higgs boson was hard enough to find at all. It appears rarely, decays almost instantly, and must be reconstructed from the particles it leaves behind. To ask whether it has internal structure is even harder. We cannot simply open it up. We cannot hold it still and inspect it. Instead, physicists study how it is produced, how it decays, how often it appears in different processes, and whether its interactions match the predictions of the standard model. If there were hidden parts or new forces involved, they might subtly alter those patterns. So far, the Higgs has been remarkably well behaved, almost suspiciously so. It keeps looking like the simple Higgs boson the standard model promised. Still, the question remains alive because the Higgs is unusual. It is the only known elementary scalar particle. Scalar means that the Higgs field has a simple kind of value that does not point in a direction in space. The Higgs boson has no spin. That makes it different from matter particles and different from the familiar force-carrying particles. In the family portrait of the standard model, the Higgs is the relative standing slightly apart, smiling politely while everyone wonders what it knows. Its uniqueness makes physicists curious. Nature does not have to provide only one scalar field. There could be more. The Higgs boson we discovered might be part of a larger Higgs sector, or it might be related to deeper dynamics not yet seen. There are theories in which the Higgs boson is not truly elementary. In some ideas it is composite, made from new, more fundamental particles held together by a force we have not discovered. In that case, the Higgs boson would be somewhat like a pion in nuclear physics, a particle that appears elementary at first glance but is actually made of quarks. Other theories suggest that the Higgs is connected to a hidden symmetry of nature, or that it has partners, cousins, or heavier relatives. Some propose that the Higgs field may be linked to dark matter, the invisible substance that seems to shape galaxies but does not shine. None of these ideas has been confirmed. They are possibilities, not established facts. But they show why the question of what the Higgs boson is made of has not gone away. The standard model answer is clear. The Higgs boson is an elementary excitation of the Higgs field. The beyond standard model question is open. Could that excitation be a low-energy sign of something deeper? Could the Higgs field itself emerge from a more basic structure? Could its apparent simplicity be hiding complexity at energies we have not yet reached? Physics holds both ideas at once. It respects the evidence we have and keeps looking for evidence we do not yet have. One reason physicists suspect there may be more to the Higgs is connected to its mass. The Higgs boson has a mass that is heavy, compared with many elementary particles, but not as heavy as some theoretical expectations might naturally suggest if unknown high-energy physics contribute strongly. This is part of a famous puzzle often called the hierarchy problem, though we do not need the technical details to feel the issue. The question is why the Higgs mass sits where it does. Why is it not much larger? What protects it? Is there a hidden principle, a symmetry, or a new layer of physics that keeps the Higgs from being driven to an enormous mass? The standard model can describe the measured value, but it does not fully explain why that value is natural. Physicists are not fond of coincidences that look too delicate. They will tolerate them, of course, because nature is allowed to be rude, but they keep checking. Supersymmetry was one proposed answer. It suggested that known particles might have heavier partner particles, and those partners could help stabilize the Higgs mass. For many years, physicists hoped the Large Hadron Collider might find such partners. So far, it has not. That does not prove the idea entirely false in every form, but it has made the simplest versions less likely. Other ideas imagine the Higgs as composite. If the Higgs is made from deeper ingredients, its mass might be explained by the dynamics binding those ingredients together. Again, no direct evidence has appeared. The Higgs remains, for now, stubbornly elementary. There is a quiet tension here. On one hand, the Higgs boson looks exactly like a fundamental particle in our experiments. On the other hand, its very existence raises questions that make physicists suspect it may be a clue to something beyond the standard model. It is a little like finding a perfectly ordinary door in a wall where no door should be. The door opens and closes properly, the handle works, the hinges are neat. But one cannot help wondering why it was placed there, and what might be behind it. To understand what made of means in this context, we should also separate the Higgs boson from the particles it decays into. This is a common source of confusion. The Higgs boson can decay into other particles, such as photons or particles containing quarks, depending on the allowed processes. But those decay products are not its ingredients in the ordinary sense. When a Higgs boson decays into 2 photons, it was not a little bag of 2 photons. When it decays into other particles, those particles were not sitting inside waiting to be released. The decay is a transformation of one quantum excitation into others, permitted by the interactions among fields. Energy and quantum properties are conserved, but the final particles are produced by the process. A decaying Higgs is not like a cracked nut revealing a kernel. It is more like a note changing into other notes because the underlying instrument allows that transition. This may feel less satisfying than a mechanical picture, but it is the way quantum field theory works. Particles are not permanent Lego bricks that can only be rearranged. They can be created and destroyed in interactions as long as the conservation laws are obeyed. The fields remain. Their excitations change. A high-energy collision can produce a Higgs boson. The Higgs boson can decay into excitations of other fields. The detector records those final excitations. From them, physicists reconstruct the brief existence of the Higgs. The whole story is written in field language from start to finish. The phrase made of energy sometimes appears in popular explanations, and it can be useful if handled carefully. The Higgs boson carries energy. Its mass is a form of energy. It can be produced from collision energy, and its decay products carry that energy away. But saying it is made of energy can also mislead, because energy is not a substance. Energy is a property of physical systems, a measure of their capacity to do work, change states, or appear as mass in particle physics. A Higgs boson is not a blob of energy floating around. It is an excitation of a specific field with specific properties. The field matters. The identity matters. Energy alone does not tell you whether you have made a Higgs boson, a photon, a quark, or a spray of other particles. The rules of the fields determine what appears. Another tempting phrase is that the Higgs boson is made of the Higgs field. That is closer, but still needs care. A wave is made of water only in the sense that it is water in motion. A sound wave in air is made of air in motion, though the sound is not a separate object added to the air. The Higgs boson is the Higgs field in an excited quantum state. It is not a chunk carved out of the field. It is not a droplet of field substance. It is a quantized disturbance. The field is primary. The boson is one possible excitation. This is also why there can be many Higgs bosons created in separate collisions, even though there is one Higgs field. The field exists everywhere. Different collision events can excite it locally. Each excitation is a Higgs boson. They're identical because they are excitations of the same underlying field. They are not manufactured individually with tiny serial numbers. One Higgs boson is not older, moodier, or more experienced than another. They share the same basic properties because the field and the rules are the same. Now, if the Higgs boson is elementary, does that mean it is point-sized? In the theory, it is treated as point-like, meaning it has no measurable spatial extent or internal structure. But this is not quite the same as saying we have proven it has literally no size in every possible sense. It means that at the distances and energies we have tested, it behaves as though it has no size. If it has substructure, it must be hidden at scales smaller than we can currently resolve or in ways not yet revealed by experiments. This is the same kind of caution physicists apply to other elementary particles. An electron is point-like as far as we know. The Higgs is point-like as far as we know. Future experiments may push that knowledge further. The Large Hadron Collider continues to refine measurements of the Higgs. Future colliders, if built, could act as Higgs factories, producing far more Higgs bosons and measuring their properties with greater precision. Such machines would not look inside the Higgs in a simple visual way, but they could reveal whether its behaviour deviates from the elementary standard model picture. A tiny difference in how often it decays into certain particles, a tiny shift in its self-interaction, a rare invisible decay, any of these could hint that the Higgs is connected to something else. The Higgs may be quiet, but precision can make quiet things speak. The self-interaction of the Higgs is especially interesting. The Higgs field does not only interact with other fields, it also interacts with itself. This self-interaction helps determine the shape of the field's energy landscape and why the field settles into its non-zero vacuum value. Measuring it is extremely difficult because it often requires studying rare events involving more than one Higgs boson. But it matters because it tells us whether the Higgs field behaves exactly as the standard model says. If the field has hidden complexity, its self-interaction might be one place where the first clue appears. There is also the possibility of invisible Higgs decays. If the Higgs boson interacts with particles we cannot detect directly, such as possible dark matter particles, then some Higgs decays might appear to produce missing energy. Physicists search for this. So far, there is no confirmed sign that the Higgs decays into dark matter or other hidden particles. But the search continues because the Higgs field could be a portal between ordinary matter and hidden sectors. Portal is a popular word here, and for once it is not entirely overdramatic. The Higgs has a special role because many kinds of particles could, in principle, interact with it without needing electric charge or colour charge. If dark matter has any connection to the Higgs boson might help reveal it. All of this means that the question what is the Higgs boson made of has layers. At the first layer, the answer is that it is not made of smaller known particles. At the second layer, it is an excitation of the Higgs field. At the third layer, we ask whether the Higgs field itself is fundamental or emergent. At the fourth layer, we ask whether new physics changes the story at higher energies. The standard model gives a precise and successful answer for the first two layers. The deeper layers remain open. There is a philosophical flavour to this, but it is not just philosophy. It is experimental. If the Higgs were composite, experiments might eventually reveal signs. If there are additional Higgs particles, colliders might produce them. If the Higgs connects to dark matter, certain decays or production patterns might betray that connection. If new symmetries protect the Higgs mass, their consequences might appear in future data. These are not idle dreams. They are testable ideas, though difficult ones. Physics is patient because the universe tends not to hand over its deepest secrets just because someone asks nicely. For the purposes of understanding the Higgs today, the safest and most accurate statement is this. The Higgs boson is a fundamental quantum ripple of the Higgs field, with no known smaller parts. It is not matter in the ordinary sense. It is not built from atoms or quarks. It is not a tiny ball. It is not the source of all mass by itself. It is the detectable excitation of a field whose background value gives mass to many elementary particles. That field is part of the structure of the vacuum. The boson is the brief ripple that confirms the field exists. This answer may feel less concrete than saying made of quarks, or made of strings, or made of tiny glowing dust. But concreteness is not always the same as truth. The universe at small scales is not obligated to resemble a collection of miniature household objects. It is described more accurately by fields, symmetries, excitations, interactions, and probabilities. The Higgs boson belongs to that deeper grammar. It is not made of stuff the way ordinary things are made of stuff. It is made of a field doing one of the things that field can do. And perhaps that is why the Higgs boson is so fascinating. It marks the place where our everyday intuition gives way to a more subtle kind of reality. We begin with a simple question about ingredients and end up talking about the vacuum, fields, mass, symmetry, and the possibility of unknown physics. We ask what is inside the particle, and the answer points outward, into all of space. The Higgs boson is not a little secret hidden inside matter. It is a brief visible shiver in an invisible field that fills the universe. Once that idea settles, mass itself begins to look different. We usually treat mass as a basic fact, the heaviness of things, the reason a suitcase complains when packed too enthusiastically, the reason a stone feels different from a feather in the hand. But at the elementary level, mass is not simply the amount of material packed into a particle. It is a property shaped by fields and interactions, and the Higgs field explains only part of the story. Ordinary matter gets much of its mass from energy inside protons and neutrons, from the restless dynamics of quarks and gluons, not directly from the Higgs alone. So the next step is to look more carefully at mass itself, because once the Higgs boson has taught us what a particle is not made of, it also invites us to ask why anything feels heavy in the first place. Mass seems at first like one of the most ordinary facts in the world. It is the reason a stone feels solid in your hand, the reason a suitcase becomes more judgmental with every extra shirt you pack, and the reason your body settles into a chair rather than drifting gently through the ceiling like a confused balloon. We live with mass constantly. We carry it, lift it, weigh it, drop it, complain about it, and occasionally pretend not to notice it when the bathroom scale has clearly been affected by local gravitational politics. It feels so familiar that it is easy to assume we understand it. Heavy things have more mass, light things have less. Simple enough. But mass is not as simple as heaviness. That is the first little crack in the familiar picture. Heaviness is what you feel when gravity pulls on something. Mass is deeper. Take the same object to the moon, and it weighs less because the moon pulls on it more weakly than Earth does. But its mass has not changed. A hammer on the moon is still just as resistant to being pushed sideways as it was on Earth. It may weigh less in your hand, but it has not become less itself. Mass is not merely how strongly Earth pulls on an object. It is also the object's resistance to acceleration, its reluctance to change motion. If you have ever tried to push a fully loaded shopping trolley with one stubborn wheel, you have met inertia in a very practical and slightly irritating form. This gives us two everyday faces of mass. There is gravitational mass, the way matter responds to gravity, and there is inertial mass, the way matter resists changes in motion. One tells you how strongly something is pulled by gravity, the other tells you how hard it is to get that thing moving, stop it, or change its direction. One of the remarkable facts of physics is that these two kinds of mass appear to be equivalent. The same property that makes something resist acceleration also makes it respond to gravity. Einstein took this equivalence very seriously, and it helped lead him toward the idea that gravity is not simply a force in the old sense, but a curvature of space and time. So even before we reach particles, mass is already wearing more than one hat. At ordinary scales, mass can be measured in a practical way. Put something on a scale, compare it with a standard, and you get an answer. A loaf of bread has a certain mass. A cup of tea has a little more mass before you drink it than after, assuming you do not spill it, which would introduce a different and less dignified experiment. This practical kind of mass works beautifully for daily life. It is good enough for cooking, shipping, engineering, medicine, and deciding whether you can carry all the groceries in one trip, which remains one of humanity's most ambitious tests of confidence. But when we ask where mass comes from at the deepest level, the simple picture begins to dissolve. It is tempting to say that mass is just the amount of matter inside something. That works roughly for bags of potatoes, but not for elementary particles. An electron has mass, yet as far as we know, it has no smaller parts. It is not filled with tiny bits of electron material. It is not a little sphere packed with substance. The electron is an excitation of the electron field, and its mass is tied to its interaction with the Higgs field. The same is true, in different ways, for quarks and other elementary particles. Their masses are not explained by hidden ingredients. They are properties that arise from how their fields behave and interact. This is where the Higgs field enters the mass story, but it does not enter in the overly simple way it is sometimes described. Popular accounts often say the Higgs gives everything mass. That sentence is short, memorable, and not quite right. The Higgs field gives mass to many elementary particles, including electrons and quarks, through their interactions with it. That is profoundly important. Without the Higgs field, the particles that make atoms possible would not have the masses they do. The universe would not have ordinary chemistry, stable atoms, familiar matter, or sleepy discussions about particle physics late at night. But the Higgs field is not the source of all the mass you encounter. Most of the mass in ordinary matter comes from something else. Your body is made of atoms. Most of the mass of those atoms is in their nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons, bound together by the strong nuclear force. Now, quarks do get their own small masses from the Higgs field, but the mass of a proton or neutron is much larger than the simple sum of the masses of the quarks inside. The rest comes mostly from the energy of the strong force, from the motion and interaction of quarks and gluons confined inside the proton or neutron. In other words, most of the mass of the matter around you is not simply the mass of tiny ingredients. It is energy held in a restless, tightly bound system. That idea is wonderfully strange. A proton is not like a small bag containing 3 heavy pebbles. It is a dynamic object, a storm of quantum fields. Quarks move within it. Gluons carry the strong force. Additional quark and antiquark pairs flicker as part of the quantum activity. The proton's mass is largely the energy of this intense internal motion and binding. It is less like weighing the bricks in a wall and more like weighing the entire tension, vibration, and stored energy of a system that never really sits still. The proton feels stable and simple to us because it lasts so long and forms the nuclei of atoms, but inside it is not calm. It is a tiny, persistent thundercloud of the strong force. This means that when you lift an object, most of what you are lifting is not Higgs given mass in the direct elementary particle sense. You're lifting energy bound inside protons and neutrons. The Higgs field is still essential because it gives mass to quarks and electrons, and without those masses the structure of matter would be different. But the dominant mass of everyday matter comes from strong force dynamics. The Higgs is crucial, but it is not working alone. Physics rarely gives one character the entire stage, no matter how good the nickname is. The connection between mass and energy is one of the deepest lessons of modern physics. We often think of mass as stuff and energy as activity, as though they are separate categories. A stone has mass. A moving car has energy. A warm cup of tea has heat energy, which is perhaps the most emotionally useful kind. But relativity showed that mass and energy are deeply related. A system with more energy has more mass. Heat something up and in principle its mass increases ever so slightly. Bind particles together and the energy of that binding contributes to the mass of the system. Release energy from a system and its mass decreases. The changes may be tiny in everyday settings, but at nuclear and particle scales they become central. This is why the mass of a proton can come mostly from the energy of fields inside it. Energy is not a ghostly extra. It contributes to the mass of a system. The strong force creates an environment where quarks and gluons are confined, moving and interacting in a way that stores energy. That stored energy shows up as mass. So the ordinary matter, is partly made heavy by activity, not by stillness. The solid world is built from restless fields. Even the word solid becomes a little suspicious here. Matter feels solid because atoms resist being pushed into one another. That resistance comes mainly from electromagnetic forces and quantum rules about electrons. When your hand rests on a table, the atoms in your hand do not truly touch the atoms in the table in the everyday image of hard little balls pressing together. Their electron clouds and electromagnetic interactions prevent them from passing through each other. The table feels solid because fields and quantum principles say, no, thank you, this arrangement will not collapse into that one. Mass gives the matter inertia, but solidity comes from other interactions. The familiar world is a collaboration. Mass is also strange because some particles have none at all. Photons, the particles of light, have no rest mass. They still carry energy and momentum, and they can exert pressure. Light can push, though very gently. A beam of light can be affected by gravity not because photons have rest mass, but because gravity and general relativity shapes the paths followed by energy and motion through space and time. So massless does not mean unreal, weightless in every sense, or incapable of influence. Light has no rest mass, yet it warms planets, carries information across the cosmos, drives photosynthesis, and wakes people in the morning when curtains have failed in their one important duty. A massless particle must move at the speed of light in a vacuum. It cannot slow down and rest. A massive particle, by contrast, can be at rest relative to something. It can move more slowly than light. The Higgs field helps explain why some particles are massive and others remain massless. Particles that couple to the Higgs field in the right way acquire rest mass. Photons do not. This difference is not a matter of photons being smaller or less substantial in a material sense. It is about the structure of the fields and their interactions. Neutrinos add another layer of mystery. They have extremely tiny masses, so tiny that for a long time physicists thought they might be massless. Their masses are far smaller than those of charged particles such as electrons. The Standard Model in its original simple form did not include neutrino masses in the way we now know they must exist. That tells us something important. The Higgs mechanism explains many masses beautifully, but the full pattern of masses in nature is not fully understood. Neutrino masses may involve physics beyond the simplest Standard Model picture. They are faint little messengers that pass through matter almost unnoticed, but they carry a sign that the mass story is not finished. Then there is dark matter. We know from the motion of galaxies, the bending of light, and the large-scale structure of the universe that there is more matter than the ordinary atoms we see. This dark matter has mass because it gravitates. It shapes galaxies and clusters. Yet we do not know what it is made of. It may be some kind of particle not included in the Standard Model. It may interact weakly with ordinary matter. It may have its own hidden fields. Does it get mass from the Higgs field? Perhaps, perhaps not. Some theories propose a connection between the Higgs and dark matter, where the Higgs field acts as a kind of bridge to hidden particles. So far, no such connection has been confirmed, but the possibility reminds us that mass is not only a solved question inside the known particle list. It may be pointing toward matter we have not yet identified. The pattern of elementary particle masses is one of the most puzzling features of the Standard Model. The electron is light. The muon, a heavier cousin of the electron, is much heavier. The tau is heavier still. The quarks span a huge range of masses. The top quark is enormously heavy compared with the up and down quarks that help make protons and neutrons. The Higgs field can give these particles mass, but the strengths of their couplings to the Higgs field are inserted into the theory from measurement. We know the pattern, but we do not know why it has to be that pattern. It is like finding a row of dials on the universe's control panel, all set to very specific positions, and being able to read the settings without yet knowing why those settings were chosen. This is a very different kind of ignorance from not knowing how mass works at all. Physicists do understand a great deal. They know how the Higgs mechanism allows elementary particles to have mass while preserving the consistency of the electroweak theory. They know how much of ordinary matter's mass arises from strong force energy inside protons and neutrons. They know how to calculate many particle interactions with astonishing precision, but the deeper why remains open. Why does the electron interact with the Higgs field so weakly? Why does the top quark interact so strongly? Why are there 3 generations of matter particles with different masses? Why do neutrinos have such tiny masses? These questions do not undo what we know. They show where the map still fades into mist. Mass also depends on context in ways that can surprise us. A bound system can have a mass different from the sum of its separated parts because binding energy matters. In atomic nuclei, for example, the mass of a nucleus is slightly less than the mass of the free protons and neutrons that make it up. The missing mass corresponds to the energy released when the nucleus forms. This is the principle behind nuclear energy in stars and reactors. Stars shine because nuclear reactions transform mass and energy, releasing light and heat over vast timescales. The warmth of sunlight on your face is connected to the fact that mass is not just passive substance. It can be converted, released, rearranged, and expressed as energy. At the level of atoms, the mass of electrons is small compared with the nucleus, but it is still essential. If electrons were massless, atoms would not behave as they do. Their mass helps determine the size and structure of atoms and the patterns of chemistry. A tiny elementary mass from the Higgs field helps shape the size of the world. The electron is light, yes, but in physics, small things can have enormous consequences. A slight change in electron mass would change atomic structure. Change atomic structure, and chemistry changes. Change chemistry and biology may never appear. The gentle mass of the electron is one of the quiet conditions that makes ordinary life possible. Quark masses matter too, even though most of the proton's mass comes from strong force energy. The masses of the up and down quarks affect the masses of protons and neutrons and the stability of atomic nuclei. Small changes could alter nuclear physics, star formation, and the elements available in the universe. The Higgs field, by giving quarks their masses, helps tune this delicate structure. Again, it is not the whole source of ordinary mass, but it plays a foundational role in setting the rules. This gives mass a layered character. At one layer, elementary particles have masses connected to the Higgs field. At another layer, protons and neutrons have masses mostly from strong interaction energy. At another layer, atoms have mass from their nuclei, electrons, and binding energies. At larger scales, objects have mass from all the particles and energy inside them. At cosmic scales, mass and energy shape the expansion, curvature, and structure of the universe. The word mass travels across all these layers, but it does not always mean a simple pile of stuff. It is a property of systems, fields, energy, and interactions. Even weighing yourself is, in a quiet way, an interaction with all these layers. The scale responds to the force between your body and Earth. Your body's mass comes mostly from protons and neutrons. Their mass comes mostly from strong force energy. The quarks and electrons inside you get their elementary masses from the Higgs field. The atoms in you are forged in stars and cosmic events. The whole process is held together by gravity, electromagnetism, nuclear forces, quantum rules, and the background value of the Higgs field. A bathroom scale may display a simple number, but behind that number is almost the entire history of modern physics, which is a lot to think about before breakfast, and perhaps a good reason to treat the scale with compassion. Mass is also what allows structure to form under gravity. In the early universe, tiny variations in density grew over time. Matter gathered into clouds, clouds formed stars and galaxies, stars created heavier elements, and those elements eventually became planets and living systems. Without mass, gravity would have nothing ordinary to gather. Without the particular masses of particles, atoms and nuclei might not form properly. The universe's large-scale structure depends on the small-scale properties of fields. The quiet details of particle masses echo outward into galaxies, and yet the Higgs field itself does not explain gravity. This is another important boundary. The Higgs field gives rest mass to certain elementary particles, but gravity responds to all forms of energy and momentum, not only Higgs-generated mass. Light gravitates. Binding energy gravitates. Dark matter gravitates. The Higgs is part of the mass story, not the full theory of gravity. Sometimes popular accounts blur this distinction, making it sound as if the Higgs field creates gravity or explains why things fall. It does not. If you drop a spoon, gravity pulls it downward because Earth's mass energy curves space and time, and the spoon follows the path set by that geometry. The Higgs field helped give some of the spoon's elementary particles their masses, but it is not the force pulling the spoon to the floor. The floor, meanwhile, remains unhelpfully where dropped spoons tend to find it. This distinction keeps the wonder honest. The Higgs field is not everything. It is not a universal answer wearing a lab coat. It is one part of a larger structure. It explains how many fundamental particles acquire rest mass. It helps complete the electroweak theory. It gives us the Higgs boson as a measurable excitation. But ordinary mass also comes from strong force energy, and gravitational behaviour belongs to the structure of space-time and the full energy content of systems. The universe is not a single trick. It is a layered set of principles that meet one another in surprising ways. So why does mass feel so ordinary when its origin is so strange? Probably because our senses live far above the level where the strangeness is visible. We do not feel quark confinement when we lift a cup. We feel weight. We do not notice the Higgs field when we walk across a room. We notice the floor, the air, perhaps the slight suspicion that we forgot why we entered the room in the first place. The deep mechanisms are hidden because they are stable and consistent. They do their work quietly, allowing the world to appear simple enough for life to navigate. Physics reveals that beneath this simplicity is a network of fields and energies that would have seemed almost unimaginable a century ago. The Higgs boson, then, does not just answer a question about one particle. It changes the way mass itself is understood. It shows that elementary mass can arise from interaction with a field that fills space. It reminds us that particles are not necessarily made of smaller things. It also points to the limits of the easy phrase that the Higgs gives mass. Yes, it gives mass to many elementary particles. No, it does not account for most of the mass of ordinary matter directly. Yes, it is essential to the world as we know it. No, it is not the whole story. The truth is more interesting than the slogan. In a way, mass is not a single mystery but a family of mysteries. There is the mystery of why elementary particles have the masses they do. There is the mystery of why the Higgs field has its particular value. There is the mystery of why the Higgs boson has its measured mass. There is the mystery of neutrinos. There is the mystery of dark matter. There is the challenge of uniting mass, energy, quantum fields, and gravity into one deeper framework. The Higgs boson gave physicists a major piece of the puzzle, but it did not complete the picture. It made the picture sharper, and by making it sharper, it made the missing parts easier to see. That may be the most honest place to leave mass for the moment, not as a simple heaviness, but as a layered property of fields, energy, and interaction. The stone in your hand feels solid because many deep rules cooperate. The atoms in your body have structure because particles have the masses and charges they do. The protons and neutrons inside those atoms carry mass mostly from the energy of the strong force. The quarks and electrons owe their elementary masses to the Higgs field. And the Higgs boson, that brief ripple in the invisible sea, is the clue that this field is truly part of the world. Once mass becomes this strange, the Higgs becomes even more intriguing. It is not merely the answer to why things are heavy. It is a doorway into questions that remain unsettled. Why this field? Why this value? why this boson? Why these particle masses? Why is the universe built with this particular pattern and not another? The Higgs field has told us enough to transform physics, but it has not told us everything. And that is where the next stretch of the journey leads, toward the quiet, unanswered questions still gathered around the Higgs, waiting in the data, in future experiments, and perhaps in the deeper structure of reality itself. The Higgs field has given physics one of its most important answers, but it has also left a surprisingly long list of questions on the table. That is often how science works. A discovery arrives, the room fills with excitement, everyone claps, someone somewhere opens a bottle of something fizzy, and then, after the celebration, the scientists look more closely and realise the discovery has not ended the mystery. It has made the mystery sharper. The Higgs boson did not close the book on particle physics. It confirmed a crucial page, and then pointed rather calmly towards several pages we still cannot read. The first thing the Higgs still has not told us is why it is the way it is. That may sound like a vague question, but in physics it becomes very specific. The Higgs boson has a particular mass. The Higgs field has a particular background value. The known particles interact with the Higgs field with particular strengths. The electron interacts weakly with it. The top quark interacts very strongly. Other particles sit between those extremes. We can measure these values. We can put them into the standard model and use them to make accurate predictions. But we do not yet know why nature chose those values rather than others. This is different from not understanding the mechanism. The Higgs mechanism explains how many elementary particles can have mass. It shows how the Higgs field allows certain particles to behave as massive while keeping the deeper structure of the theory consistent. That is a powerful explanation, but it does not explain the whole pattern. It tells us how the machine works once the settings are given. It does not tell us why the dials were set exactly where they are. It is a little like being handed a beautifully built clock, understanding how the gears move, and still wondering why it was set to this particular time when you found it. The masses of elementary particles are especially puzzling because they vary so widely. The electron is light, the muon is much heavier, the tau is heavier still. The quarks range from very light to extremely heavy by particle standards. The top quark is so heavy that it stands out dramatically from the rest. The Higgs field is involved in giving these particles their masses, but the standard model does not explain why the interactions have that particular pattern. Physicists call this the flavor problem, although the word flavor here has nothing to do with soup, ice cream, or regrettable crisps. It refers to the different types of matter particles and the strange pattern of their masses and mixings. Why should there be 3 generations of matter particles? Why do the heavier generations exist at all? Ordinary matter around us is made mainly from the lightest generation, electrons, up quarks, and down quarks. The heavier cousins appear in high-energy processes and then decay. They are real, measurable, and important, but they are not needed for building chairs, stars, or sandwiches in the ordinary sense. Nature includes them anyway. The Higgs field gives them mass according to their interactions with it, but the deeper reason for this family structure remains unknown. The Higgs is part of the answer, but not the reason for the pattern. Then there is the question of the Higgs boson's own mass. The Higgs is not massless. It has a measured mass, and that mass fits the standard model beautifully in one sense. But from a theoretical point of view, the value is puzzling. The Higgs boson is sensitive to possible physics at much higher energies. If there are unknown heavy particles or deeper processes, they could influence the Higgs mass in ways that might naturally make it much larger than what we observe. Yet the Higgs sits at the measured value. This has led physicists to wonder whether something protects it, something we have not yet discovered. This puzzle is often called the hierarchy problem. The name sounds as if it belongs in an office management seminar, perhaps one involving charts and someone named Trevor explaining workflows. But in physics, it is a deep question about why the weak scale, where the Higgs field does its familiar work, is so much smaller than other enormous energy scales that may exist in nature. If the Higgs mass needs delicate adjustment to stay where it is, physicists become suspicious. They do not reject the possibility, because nature is allowed to be delicate. but they wonder whether a hidden principle is at work. For many years, one of the most popular possible answers was supersymmetry. This idea proposed that every known particle might have a partner particle with different quantum behavior. These partner particles could help cancel the effects that would otherwise make the Higgs mass unstable. It was an elegant idea, and it also offered possible dark matter candidates. Physicists looked for signs of supersymmetry at the Large Hadron Collider. So far, no confirmed evidence has appeared. That does not erase every version of the idea, but it has made the simplest expectations less comfortable. The Higgs has remained polite, quiet, and stubbornly standard model-like. Another possible answer is that the Higgs boson is not truly elementary. Perhaps it is composite, made from deeper ingredients bound by a new force. In that view, the Higgs would be somewhat like a proton or a pion, appearing simple at low energies while hiding internal structure at smaller scales. This could help explain why its mass is what it is. But again, experiments have not found evidence for compositeness. The Higgs behaves like a point-like elementary particle within current limits. If there is deeper structure, it is hidden beyond the reach of present measurements, or it works in a more subtle way than our current searchers can see. The Higgs has also not told us whether it is alone. The standard model contains one Higgs field and one observed Higgs boson. But many theories beyond the standard model include more. There could be additional Higgs fields, heavier Higgs bosons, charged Higgs bosons, or other scalar particles related to the one we have found. Nature may have given us one simple Higgs, or it may have given us the first visible member of a larger family. Physicists continue to search for these possibilities. So far, no additional Higgs particles have been confirmed. This question matters because the Higgs is the only known elementary scalar particle. That makes it unusual. Matter particles have their own kind of quantum behavior. Force carriers have another. The Higgs stands apart. It has no spin, no electric charge, and a role unlike the others. It is not unreasonable to wonder whether one such particle is the whole story or only the simplest visible piece. If future experiments found another Higgs-like particle, it would immediately reshape our understanding of the field, the standard model, and possibly the early universe. The Higgs field also has not told us exactly how it behaved when the universe was very young. Today, the Higgs field has a steady background value throughout space, but in the extremely hot early universe, conditions were different. At high enough temperatures, the electroweak symmetry may have been restored, meaning the Higgs field had not yet settled into its present state. As the universe cooled, the Higgs field changed into the state we know today. That transition may have been smooth, or it may have happened more dramatically depending on physics that may or may not extend beyond the standard model. This matters because a dramatic electroweak transition could have helped explain one of the biggest mysteries in cosmology. Why is the universe made mostly of matter rather than antimatter? In the early universe, matter and antimatter should have been produced in nearly equal amounts. When matter and antimatter meet, they can annihilate into radiation. If the balance had been perfectly equal, the universe today might contain very little matter at all. Yet matter survived. Stars, planets, and people exist because something tipped the balance. The standard model contains some ingredients that distinguish matter from antimatter, but not enough to explain the observed imbalance. The Higgs field may have played a role if the early electroweak transition had the right properties, but the simplest standard model does not seem to make that work. So the Higgs is close to the question, but it has not answered it. There is also dark matter, waiting quietly in the background of nearly every modern physics discussion, rather like a guest at a dinner party, who says very little, but clearly owns most of the furniture. Dark matter appears to make up a large fraction of the matter in the universe. We infer it from gravity, from the motion of galaxies, from galaxy clusters, and from the large-scale structure of the cosmos. But we do not know what it is. It does not shine. It does not interact with light in the usual way. It is not made of ordinary atoms. Could the Higgs help reveal dark matter? Possibly. The Higgs field has a special role because many kinds of new particles could interact with it. Some theories propose a Higgs portal, a connection between the Higgs field and hidden particles that do not interact much with ordinary matter. If dark matter particles couple to the Higgs, then the Higgs boson might sometimes decay invisibly into them, leaving missing energy in detectors. Physicists search for this. So far, there is no confirmed sign. The Higgs has not yet opened that hidden door, if the door is there at all. Neutrinos add another unanswered question. These very light particles are known to have mass, but their masses are tiny compared with those of other matter particles. The original Standard Model treated neutrinos as massless. Their observed masses require an extension of the theory. The Higgs field may be involved, but the mechanism may not be the same simple pattern used for charged particles and quarks. There may be heavy unseen neutrino partners. There may be a deeper explanation connected to physics at very high energies. The Higgs has shown us how many particles gain mass, but neutrinos remind us that the full mass story is still incomplete. The Higgs also has not told us whether our vacuum is ultimately stable. This sounds dramatic, and it is best handled calmly. Based on the measured masses of the Higgs boson and the top quark, our universe may sit near a boundary between different possibilities for the long-term behaviour of the Higgs field. It may be completely stable, or it may be metastable, meaning the vacuum we live in could be a long-lived state, rather than the absolute lowest possible state. If it is metastable, it would still be enormously long-lived, far longer than any timescale relevant to ordinary life. So this is not something to worry about while brushing your teeth. The toothpaste has enough problems of its own. But scientifically, the question is profound. The value of the Higgs field defines part of the structure of the vacuum. If there were a deeper vacuum state somewhere in the field's energy landscape, that would tell us something important about the universe. It might mean the Standard Model is only part of the story. It might mean unknown physics at high energies changes the conclusion. Precise measurements of the Higgs and the top quark are needed to understand this better. The Higgs has not yet told us whether the vacuum is stable in the deepest possible sense. Another missing piece is the Higgs self-interaction. The Higgs field does not only interact with other fields, it should also interact with itself. This self-interaction determines the shape of the field's energy landscape and helps explain why the field settles into its present value. We have discovered the Higgs boson, and we have measured many of its interactions, but the self-interaction remains difficult to measure directly. One way to study it is to look for events that produce pairs of Higgs bosons. These events are rare and hard to separate from background processes. Future experiments may measure them more precisely. Until then, we do not fully know whether the Higgs field self-behaviour matches the Standard Model exactly. This is not a minor detail. The self-interaction is tied to the deepest structure of the Higgs field. If it differs from prediction, that could point toward new physics. It could affect our understanding of the early universe and the electro-weak transition. It could reveal that the Higgs field is more complicated than the simplest model suggests. The Higgs boson we have found is like one small wave on the surface. To understand the whole field, physicists need to know how the field responds to itself. There is also a broader question the Higgs has not answered. Why is there a Higgs field at all? In the Standard Model, the Higgs field is included because it works, and because experiments confirm its consequences. But why does nature contain this kind of scalar field with this kind of vacuum value? Is it fundamental, or does it emerge from deeper principles? Is it connected to grand unified theories, where forces become related at extremely high energies? Is it connected to quantum gravity? Is it connected to inflation, the rapid expansion thought to have occurred in the early universe? These are open questions. The Higgs may be a local piece of a much larger structure, or it may simply be one of nature's basic facts. We do not yet know. The connection to inflation is especially tempting but uncertain. Cosmologists think the early universe may have expanded extremely rapidly in a tiny fraction of a second. This process is often described using a field, sometimes called the inflaton. The Higgs field is also a scalar field, which naturally leads people to wonder whether the Higgs could be connected to inflation. Some models explore that possibility. But the evidence is not settled, and the simplest statements are not enough. The Higgs we have measured at particle colliders may or may not be tied to the field that drove cosmic inflation. It is an intriguing possibility, not a confirmed answer. The Higgs also has not helped us combine quantum physics with gravity. The Standard Model is a quantum field theory, and it describes three of the fundamental interactions with extraordinary success. Gravity is described by general relativity, which treats gravity as the curvature of space and time. These two frameworks do not yet merge into a complete theory of quantum gravity. The Higgs field lives within the quantum field theory side of the story. It contributes to mass, and mass energy affects gravity. But the Higgs does not solve quantum gravity. It does not explain what happens inside black holes, or at the very beginning of the universe, or at the smallest possible scales where space-time itself may become quantum. The Higgs is a major piece of known physics, not the final key to everything. This is part of why the name God particle has always been so misleading. It makes the Higgs sound like the master particle that explains all reality. It does not. The Higgs boson is important because it confirms the Higgs field and completes a central part of the Standard Model, but it does not explain dark matter. It does not explain dark energy. It does not explain gravity. It does not fully explain neutrino masses. It does not explain why the particle masses have their specific pattern. It does not explain why the universe began in the way it did. It is not a magic bead at the center of existence. It is a real, specific, measurable particle associated with a field that plays a crucial role in the structure of matter. That is already extraordinary. It does not need an overexcited nickname wearing a cape. The next stage of Higgs research is less about discovery in the loud sense and more about precision. Physicists want to measure the Higgs boson's properties with increasing accuracy. They want to know whether it couples to every particle exactly as expected. They want to search for rare decays. They want to measure its self-interaction. They want to look for signs of additional particles. They want to know whether the Higgs is a portal to hidden sectors. This work is slow, careful, and often statistical. It does not always produce dramatic headlines, but it is exactly how new physics may appear. Not as a sudden glowing object on a screen, but as a small mismatch between prediction and measurement. A tiny mismatch can be enough. Many great discoveries began as small discrepancies. The universe is not always theatrical. Sometimes it whispers in the 6th decimal place and expects someone to be paying attention. That is why particle physicists build enormous detectors, collect vast amounts of data, and argue very carefully over uncertainties. The Higgs may already be telling us something beyond the Standard Model, but if it is, the message is faint. More data and better machines may be needed to hear it. Future colliders could be built specifically to study the Higgs in detail. A machine designed as a Higgs factory could produce large numbers of Higgs bosons in cleaner conditions than proton collisions. This would allow more precise measurements of its interactions and decays. Other proposed colliders could reach higher energies, searching for heavier particles connected to the Higgs, or testing whether it has hidden structure. These projects are ambitious, expensive, and technically demanding. But if the Higgs is a doorway to deeper physics, future experiments may be the way to open it. For now, the Higgs stands in a curious position. It is both a triumph and a question mark. It confirms the Standard Model, yet it points to the Standard Model's limitations. It explains how many elementary particles get mass, yet it does not explain why their masses form such a strange pattern. It appears elementary, yet physicists keep asking whether it might be composite. It helps define the vacuum, yet leaves open whether that vacuum is stable. It may connect to dark matter, inflation, or matter-antimatter imbalance, but none of those links has been proven. There is a quiet lesson in that. Understanding is not always the same as finishing. The discovery of the Higgs boson was one of the great achievements of modern science, but it did not make physics smaller. It made physics larger. It gave us a confirmed field that fills space, a particle that ripples from it, and a framework for mass at the elementary level. Then it left us with deeper questions about why the field exists, why it has its particular value, and what else may be connected to it. So what is the Higgs boson really made of? In our best current understanding, it is not made of smaller known parts. It is a quantum excitation of the Higgs field. That answer remains the anchor, but around that anchor, the open sea is wide. The field itself may be fundamental, or it may be part of a deeper structure. The boson may be alone, or it may have relatives. Its behavior may match the standard model perfectly, or tiny deviations may appear as measurements improve. The Higgs has spoken clearly enough to confirm its existence, but not clearly enough to tell us the whole story. And perhaps that is a fitting place to end our quiet journey through the Higgs. We began with a famous particle, and found that it is not really a tiny lump of stuff. It is a ripple in a field. We followed that field into empty space and found that emptiness is not truly empty. We looked at mass, and found that heaviness is only the everyday surface of a much deeper structure. We asked what the Higgs is made of and learned that the answer depends on the strange language of quantum fields, where particles are not always built from parts, and where a brief disturbance can reveal something spread across the universe. The objects around you may feel ordinary again now. The chair, the blanket, the cup, the quiet room, the phone or screen nearby. But perhaps they are a little less ordinary than before. Their atoms rely on particles whose properties are shaped by fields. Their mass comes from a mixture of Higgs interactions and strong force energy. Their solidity comes from quantum rules and electromagnetic forces. The familiar world is still familiar, but underneath it is this hidden machinery of fields, symmetries, and interactions working without fuss. If you have drifted with this thought all the way here, then maybe the Higgs has done something useful beyond physics. It has reminded us that reality can be steady and strange at the same time. A table can be solid enough to hold a cup while also being made of quantum fields. Empty space can look blank while carrying the background value of the Higgs field. A particle can vanish almost instantly while still changing our understanding of the universe. The world does not have to choose between being ordinary and being astonishing. It is both, very quietly, all the time. So wherever you're listening from tonight, and whatever small piece of matter is nearest to you, perhaps a pillow, a book, a glass of water, or your own resting hand, it belongs to this same story. It exists in a universe where fields fill space, where mass has layers, where the Higgs field sits quietly in the vacuum, and where one brief ripple gave physicists a glimpse of something fundamental. There is still so much the Higgs has not told us. But what it has told us is already enough to make the room around you feel gently connected to the deepest experiments humans have ever built. If this slow walk through the hidden side of matter brought you a little calm, or gave your thoughts somewhere peaceful to settle, I would be very grateful if you gave the video a like and subscribed. It helps this quiet corner of physics reach others who might enjoy learning about the universe at a softer pace. And as you rest now, perhaps let the Higgs remain not as a headline or a nickname, but as a small ripple in an invisible field, a clue from the vacuum, a reminder that even the simplest question, what is this made of, can lead all the way down to the foundations of reality. Sleep well, fellow traveller, wherever you are, and whatever fields are quietly holding your world together tonight.